Okay, here we are. Hi, Razvan. Hi, Andrea,
Hello.
Matthias, Joost, Pau. Hi, everyone. So we are already live streaming on YouTube, and we're gonna start soon.
Okay, perfect.
Hi, Saina. Welcome.
Hello. Good morning, guys.
Morning, morning,
Hi,
everyone.
how are you? Good to see you.
Hi, Saina.
Hello, 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 everyone.
So we're gonna be waiting just 5 minutes, and then we will start since we have this packed schedule ahead of us, and we are already live. So keep your manners.
So I think I'm going first. Should I start sharing my slides or?
So maybe you can test it. Razvan, I will just give an opening remarks, a talk of 10 minutes.
Oh,
before,
right.
But if you want, you can test it already since we're here, the system. But it's a simple Zoom call, so you should be able to,
Okay.
share the screen and yes.
Okay, so this should be, okay, I'll stop.
Perfect,
okay,
perfect. Thanks, Razvan. That's good. We are ready with 60 ghosts, apparently, followers on our YouTube live. So hi, everyone. we see you somehow. Okay, thanks to those who connected up to this point. We're gonna wait just a couple more minutes and then we start. I know this is a bit difficult to do for many people that are watching this maybe from different time zones that are not lucky enough to be aligned with the start of the workshop, but we made sure that you'll be able to see essentially all the content of the workshop online through the Continual YouTube account as recordings, through the official website of the workshop. And so be sure that you will not miss anything, I guess. And all our speakers and authors and organizers, I think, are available if you want to question them about something that they say during the workshop. So don't worry about that. Then, as I was saying, we wait just another minute because I know that some people are just connecting now and they may have some troubles maybe with the connections. And then we will start with the actual workshop. Okay, I will try now to share my screen and screen. Yep. And, oh, sorry. Oh, that was wrong. And you can tell me maybe, Andrea, if you can see my screen and my slides.
Yes, perfect.
Okay, that's perfect. So welcome all to the second edition of the Continual Learning in Computer Vision workshop at CVPR 2021. These are the opening remarks of the workshop. So welcome all. And to start, I'd like to thank all of the people that helped with the organization and the workshop itself, like our sponsors, Continual AI, Weights and Biases, Huawei, Element AI, a ServiceNow company, and Clink. That was fundamental. And I really want to thank you all for your support, without whom, it would have been impossible to do a workshop like this. That you're gonna see, it's fully packed. It's almost 8 hours content. And I think it's gonna be a very interesting event for all of you that are more experienced with continual learning, but also for people that are just starting out, like students that will be able to gather insights about recent and future trends of continual learning and maybe inspire your research. So yeah, I wanted just to thank a bit more Continual AI, which is this nonprofit research organization which helped us to at least handle all the financial transactions and really put together an awesome community that it's really supporting in the organization of the workshop. So I just wanted to spend a couple more words on it. But let's start to just quickly introduce the main topic of the workshop. I mean, all of you, most of you are experienced about this, but I just wanted to say a couple of sentences about the main effort and main field that we're trying to cover in this workshop. That is continual learning. Continual learning is being defined in several different ways, but I think more generally we can say that is this idea of making machines learn over time from a never-ending stream of data. And essentially this idea of moving a bit away from this very rigid separation of training a model offline and then deploying the same model with frozen learning capabilities and moving towards this more natural way of learning where we constantly update our model, our biased understanding about the external world over time, always improving and generalizing. And this is the main idea, the main vision behind continual learning. Then there are different facets that I hope we can explore during this workshop. But I just wanted to stress out the fact that I think all of us pretty much convey that we're not talking about a nice add-on, like an incremental feature we can put on top of our systems, but rather something fundamental, I would say, paradigm changing approach to machine learning itself. It's really changing the fundamental may change the fundamental of the field itself. And I love this quote from Ava Siegelman that is actually saying this: we're not looking for incremental improvements in state-of-the-art AI neural networks, but rather paradigm changing approaches to machine learning that will enable systems to continuously improve based on experience. So I hope this workshop will somehow help us tackle also these very visionary aspects of continual learning. But especially looking through the submissions of the different authors from all over the world, I think this workshop will help focus on these relevant questions that will be definitely addressed through the different papers we're gonna have. We're gonna look through and in poster sessions, in orals, hopefully also during the invited talks. And essentially, we, I think, have witnessed a kind of a shift from a task incremental settings that were pretty predominant, I would say, last year and the previous years, to settings like class incremental learning that is definitely more challenging, I would say, and is, I think, the most used setting in these in the papers at least submitted to the workshop, so in computer vision. Then we're going to explore also the relationship between continual learning and concept drift, which is something that it's totally relevant, but somehow it was not really explored in recent advances of continual learning in deep learning. And then we're going to have also the opportunity to explore some libraries and tools that we can use for continual learning, for speeding up our research and build on top of each other work and even reproduce results maybe more easily. Then other two important topics I think that we're going to see are the idea of lowering, finally, the amount of supervision in our continual learning systems, and to solve problems, especially in computer vision, that are not just focused on object recognition. For example, we're going to talk about object detection and question answering systems and other tasks as well. So what are the workshop stats? Because I think it's relevant to somehow have an overview of our community and our efforts. I mean, not because this workshop is representative enough, but can give us a nice idea on what's going on, especially within the computer vision, let's say, field. So we had 46 different submissions. This is like an increase of 24% with respect to last year. This is great. And all of these, of course, are full length papers, like in CVPR style. So they are very, content-wise, they're very big submissions. And of those, we accepted 23 papers accepted for the proceedings. And we have reduced somehow the acceptance rate of 12 percentage points with respect to the previous year. So we are happy about the improvement that we have seen in these, at least these two stats. And we also accepted the 16 papers that were like borderline, and but somehow we found them relevant to be showcased within the workshop. And you can find them in the accepted page, papers page in our official workshop if you want to find more about those. Then we have seen, 4 papers actually on continual learning software libraries. So this is something great, I think, and it showcases, I think, the maturity of our field that is growing fast, I believe, and is come to a point where we were producing, let's say, meta research and meta tools to help researcher achieve better results in continual learning. So that's great. And again, something that I noticed is that most of the submissions in this workshop are focusing on class incremental learning. So I guess we will discuss about this also in the panel. And how the program of the workshop is going to unfold, like this one. So first of all, I created this QR code. So if you want to get the program into your smartphone and you want to carry around you can just point your camera to this QR and you can get the full program. But essentially, we're going to start after the opening remarks with the opening talk by Razvan Pascanu. Then we're going to hear from Edis Guns, Joost van de Weijer. Then after the poster session, the coffee break, we are going to have 2 additional invited talks from Rehg and Rehg Al-Jundi. Then an oral of the only 2 accepted papers as orals. A tale of 2 CLs, the connections between class incremental learning and class, imbalanced learning and beyond. So then after a lunch break of around 1 hour, we're going to hear from Saina Ibrahimi, Andreas Tolias, and then we're going to have like a not to miss event for the panel discussion managed by Pau Rodriguez, with Rahaf Alijundi and Jeff Kloon, Eric Eton, Adis Guns, Andreas Tolidas, Sinai Raimi, and of course, if you are an invited speakers to the event, you can feel free to join the panel. I think you can all give a wonderful contribution to the discussion you're going to have. Then after the poster presentation that we put there for satisfying another time zone, we are going to hear the second talk, second oral, that is selective replay enhances learning in online continual analogical reasoning. Then a couple more invited talks by Eric Eaton and Jeff Kloon. Then the challenge presentations and the awards announcement and closing remarks by Massimo Caccia and Paolo Rodriguez. So this is pretty much the workshop content. It's a lot, and I hope we will have a lot of fun with it. And here are some tips on to make this a pleasurable experience for everyone. So you can follow the live, as I guess you're doing already if you're hearing me on YouTube. Is divided in two parts. So after 6 hours, we're gonna have like this lunch break, and then you're gonna click essentially on another link on YouTube to access the second part of the next, let's say, 5 hours content. Then you can interact if you're an attendee through the Discuss chat on our official website, where you can watch it live as well. We have an embedded video there. And you can interact through the Continual AI Slack workspace and the YouTube live comments. So all the organizers that are following you around the workshop will make sure that we convey the questions and interactions to the main Zoom room where the organizers and the speakers live, so that we can ask the correct questions. And then if you have any problem, don't hesitate to contact us. I mean, we are here to satisfy anything, any question that you may have. So contact me at vincenzo.lomonaco@unibo.it, and feel free to reach out to the organizers if you have any problems. Then please close your camera and mic if you're not talking. This is especially related to the Microsoft Teams poster sessions, where you're going to be able to interact with the speakers. All right. So that said, sorry about the length of the opening remarks. And thank you for your patience. And I would like to thank again all the organizers here. You can see how many amazing people helped us in the organization of this event. I hope you can get in touch with them, and you can interact with them during the workshop. You can interact with the other attendees, and I hope you will enjoy the event. Thank you so much. So Razvan is already here. He will be our first speaker of the day. So Razvan, you can try to share your screen and your slides. And for those of you that don't know Razvan, that I guess it's unlikely, but I'm still gonna introduce him. Razvan is a research scientist at DeepMind, and he holds a PhD from University of Montreal, which he did under the supervision of the Turing Award, Yoshua Benjo. He's very, very experienced in all aspects, I would say, of continual learning, and especially from an optimization point of view, and has been one of the leading authors of the seminal paper, Overcoming Catastrophic Forgetting in Neural Networks, introducing the AWC strategy algorithm, which has now accumulated more than 2,000 citations, I would say. So Razvan, thanks for being here. Thanks for accepting our invite and opening our workshop. So the stage is yours.
Thank you so much. And hello everybody. So yeah, I've put, as one usually does, I've put the slides together relatively in a short time. So hopefully they would make sense. So I wanted to start by defining continual learning, and that's what Vincenzo did as well in the opening words. And maybe there is a reason why many of the talks on continual learning usually start with this definition of continual learning. And that's basically because we haven't yet figured out all aspects of continual, or we haven't figured out exactly what continual learning should stand for. So in my view, the typical way of defining continual learning is to view it as a paradigm, as a protocol, right? So it's a protocol of what you're supposed to do in order to test your system in a continual learning setting. And this usually involves having a non-stationary environment, usually given as a sequence of tasks that you have to learn one after the other. And there are a lot of variations, right? So you can have different kinds of task transitions. So they can be smooth, they can be discrete. We have task repetitions. The type of task can change. So we have the task could be unsupervised. Each task could be some sort of unsupervised learning task. The typical supervised scenario, or it could be reinforcement learning. There could be no task at all. There could be just a change in the distribution. The goal of continual learning, say in comparison to curriculum learning, is that you don't actually control the environment, so you don't have any control on the sequence of tasks. What you need to do is you need to be able to learn as well as possible given the sequence of tasks. So this is different where in curriculum learning, the focus in my view, it's more on if I have these tasks, how should I order them in such a way that learning gains as much as possible from the sequence of tasks. And the second part of the protocol is what you evaluate, or what do you expect from a solution to continual learning, what it's supposed to do. And this, again, it's relatively complicated. It's usually given as a list of desiderata, right? So you have things like you should have no access or minimal access to the previous tasks. Your model should not increase capacity as it moves from one task to another. It should be able to adapt very fast to new tasks, and it should be able to recover performance. If possible, there should be no catastrophic forgetting. So catastrophic forgetting is when you've learned task A and you move to task B, and you start learning task B, you want to maintain performance on task A. So you don't want to suddenly forget everything you've learned before. You should maintain plasticity. And there's now recent works that have been showing that there could be potentially issues with plasticity. And what we mean by this is after you've learned task A and then you move to task B, you want to be able to learn task B as well as before. So there's recent works that have shown, so I'm thinking particularly of the paper from Jordan Ash and Ryan Adams, but there are others that have shown that after you've pre-trained on a task A and now you move and learn a task B, actually you end up not generalizing as well as if you just learn task B from scratch. So it seems that pre-training, or it seems by learning previous tasks, you're somehow sacrificing some part of your ability to generalize. And if this becomes, it's a new emerging problem. If this becomes really problematic, then it's definitely something that we need to think about, and we need to address and understand of why we're losing this ability to generalize if we have a model that's been pre-trained. And you want to maximize forward and backwards transfer. And I guess the reason why most papers and most talks on continual learning usually start by defining what continual learning is because there's a lot of contradictions, there's a lot of dilemmas. So some of these desiderata, they're in contradiction with each other, right? So you can't expect to have no forgetting, so you have perfect recall on everything that you've learned before while you have fixed capacity, at least not in a lifelong learning scenario where you have many tasks, right? The same about forward and backwards transfer. They're also like usually there's a lot of interference between this. So what you really want when you do when you build a continual learning solution, what you really need to do is you need to find some kind of trade-offs. You need to sacrifice a bit of something to gain something else, right? So you're willing to accept some loss in your ability to generalize in order to remember multiple tasks. So you're willing to sacrifice, I don't know, forward transfer for catastrophic forgetting, or model size for catastrophic forgetting, or any combinations of this. And it's not clear what are these trade-offs, like what are the trade-offs that we want. We can obviously build our own algorithms that do different kind of trade-offs and argue that for the setting of trade-offs that we set up, this algorithm is optimal, but then what do we actually need? And this is sort of the reason in my mind why we have this proliferation of variants of continual learning, right? They're trying to address different trade-offs. They're trying to look at different angles of the problem. And in my mind, this cannot be resolved without potentially answering two questions. So one is fixing out what problem we want to solve. So the domain, and it could very well be that a solution for continual learning, say for a classification system that is learning, interacting, learning online, interacting with the world, would potentially need to do very different trade-offs, say from a chatbot or from an RL system. So it could be that there's no one solution that will fix everything, but actually tailored solutions for different domains and different kinds of data and different kinds of aspects of continual learning that we care about. So, and this is additionally problematic because a lot of the continual learning research is typically done on benchmarks, on artificial benchmarks, that doesn't allow us to understand sort of realistic trade-offs that we would need in practice. And I think at other workshops as well, there's been lots of discussions about benchmarks and the need of new data sets that are more realistic and the need to identify applications right now that we can tap into and that require continual learning solutions just for us to experience the kind of trade-offs that we would need in realistic scenarios, rather than trade-offs that we artificially build by arbitrarily picking a sequence of tasks and putting them in a particular order. The other question that I think it's important for us to figure out these trade-offs and to figure out sort of and to motivate particular flavors of continual learning that we might want to study is to answer the question of why do we trying to do continual learning? What aspect, what real problem do we want to learn? So we want to solve. So in my mind, continual learning, it's a protocol that allows you to study sort of the learning dynamics of neural nets. It allows you to understand how learning progresses. And then the question is, what aspect of the learning of the neural net we want to actually fix, or we want to improve, or we want to change. And there are many reasons for why someone might want to work on continual learning. So I've tried to put a list here. There's definitely a lot more, and it's I think it would be an interesting exercise for someone to try to write down all the different reasons why someone might want to work on continual learning. But one particular aspect of this that I'm interested lately, and it's not just me. I've seen a lot of people started talking a lot about this quite a bit. Is this idea that continual learning promises us to the ability of building systems that can learn very efficiently. So usually the way we're thinking about this is that if you have a continual learning system, a continual learning solution, what it should be able to do, it should be able to accumulate knowledge over time. And then whenever it gets a new task, it should be able to reuse this knowledge in an efficient way to learn faster. Sort of this is connected to how we think humans learn and how we would like the systems to learn as well, right? You build on the knowledge you have already. So this is what the promise of continual learning. And usually the way I've, if I look back historically, the way I think about it is we started with this thinking. This is sort of was what we wanted to do. But then the first hurdle that you see, the first wall that you hit is the fact that the systems forget catastrophically. So then we thought, like, okay, we need to fix catastrophic forgetting so that we can have this accumulation of knowledge so that after that we can benefit from it and learn faster. And I want to talk a little bit, so maybe some of you have already seen this particular slide or this discussion, but I want to talk about why this is not really happening, or at least not straightforwardly happening. What aspect of learning is interfering with this story of accumulation knowledge? And one way to think about it is basically going back to stochastic gradient descent. So I'm going to go relatively fast through this because I assume many of you know this, but just to, and it's also quite basic, but I think it's quite useful to think about in these terms, and it's kind of explaining some of the underlying machinery that is going on in stochastic gradient descent that creates this catastrophic forgetting problem. So the tug-of-war dynamics perspective here is basically saying that a big reason why continual learning is a challenge for deep learning is because of gradient-based learning. And the way to think about it is, if you think of what gradients are doing, a gradient, computing the gradient for a particular example is equivalent of asking independently for each parameter the question, what would happen if I increase this parameter a little bit? Would the loss be smaller or bigger? So, should I increase or should I decrease? So you're asking independently for each parameter this question. And then when you have a mini batch, what you're doing is you're basically averaging the answers. So you can think of this as basically every example voting of like, oh, I want to increase this parameter, I want to decrease this parameter, and then you average them. And what this does is creates a sort of tug-of-war dynamics, right? Each example is pulling on a parameter either to increase or to decrease. And the answer at the end comes from like some sort of equilibrium that gets established, right? Everyone pulls on the parameter in one direction, and at some point you get an equilibrium, and that's sort of when learning happens. Now, the issue why this leads to catastrophic forgetting or creates all these kind of issues is that if any of these examples are not presented, are not present when you're trying to enact this game, at least not present in expectation, then the opponent would be able to pull the parameter all the way towards itself, right? To be able to either increase or decrease the parameter to whatever value it wants. And this is sort of what leads to catastrophic forgetting, right? So in gradient descent learning, the way it works is basically everyone is pulling on the parameters one way or another, and you need to have everyone present pulling on their parameters such that the needs of all examples will be present in the solution. Otherwise, if someone is absent, the other ones will be able to pull on the parameters all the way to themselves, and would not, basically the tug-of-war game would not exist. And this leads to a lot of inefficiency. At least sort of that's my personal view at the moment. And to think about why this happens is, like, you can think of this as the level of examples, you can think of it as the level of task, or it's exactly the same story. But what happens is sometimes some of these examples, you get to learn them relatively fast. So learning is not happening at the same time throughout the entire, for all your data set. And there's been, plenty of works that are looking at this, and for example, looking at ImageNet and seeing that there's a subset of examples that are actually really hard to learn and a subset of examples that are easy. But the problem is, even after you've learned something, you can't remove it from this. So you can't stop computing gradients or looking at those examples, right? Because of this tug-of-war dynamics, if some of those examples disappear, then the other ones will be able to pull the parameters all the way to themselves, and you'll get sort of this forgetting effect. So what happens is that even though you learn things at different time scales, because of gradient descent in typical IID settings, you need to rehearse everything that you see all the time. And this is what, in my view, makes deep learning extremely inefficient. Not data inefficient, but like learning inefficient, computationally inefficient. The fact that even things that have been learned, you still need to rehearse them until you fully converged. And just to add on this, you could ask the question of what happens if I have two tasks, like I mean, it's nice to think in terms of tasks. You can think like whatever task you're doing, you can always decompose it into subtasks. But the question is, what happens if I have subtasks that are equally hard? Will I still see this kind of dynamics? And I think the answer is yes. And actually, there are some works that are noticing the fact that even though you have tasks that are are equally hard by construction. So we've played with, for example, with bandits, where each bandit is basically the same problem, has the same number of arms, but they just sort of just have different contexts. So you just need to pick different arms. What you see is, even in these kind of scenarios, learning tends to learn things sequentially, which I think it's actually quite an interesting observation, right? We kind of have this intuition that in machine learning, compared to human learning, the optimal thing to do is multitask. In machine learning, the best thing is to put everything together, and that will give you the best solution. But then if you try to look at the learning dynamics and you're trying to see how you learn, it turns out that these systems also learn sequentially. Like, even though you show all the different tasks at the same time to the neural net, the neural net will learn them one by one in some random order, depending on difficulty and initialization and so forth. But it will for many occasions, it will not just learn them simultaneously. So it will learn exactly like a human does. But the difference is, even though it learns them sequentially, you still have to present all the tasks all the time, because as soon as you take one task out of the mixture, you will forget it, right? Because of this sort of tug-of-war dynamics. And I guess the reason I went over all of this is because if you're taking sort of this perspective, what is nice is you can find a different way of phrasing continual learning, which I think might even help us figuring out what kind of trade-offs we want. So you can think of what's going on is that, in a neural net, you need to do this credit assignment problem. So this is a fundamental problem that you need to do whenever you have a system that is trying to learn. And the credit assignment problem is basically deciding which parameters are to be blamed by for the loss, right? Which parameters need to learn which features. And the way this is done through a tug of war. But what continual learning is basically a study of an alternative way of doing credit assignment. Or this could be one goal of continual learning. Finding a different credit assignment that doesn't rely on this tug of war dynamics, and therefore doesn't require all the data to be present all the time. And if you're able to do this, then what you can do is you can learn a lot more efficiently. And then you end up having this accumulation of knowledge, and you end up having this behavior where you build on the knowledge that you have. And this can have implications in, natural learning, in the kind of learning we kind of hope to have these systems work on, in a system that's deployed in the real world and learns as it interacts with the world. But it can have huge implications even in the standard batch learning or ID learning, that we normally do. Like you could get to that point where, you don't need to do, 30 epochs of ImageNet. You don't need to revisit all the data through all of those epochs, right? Once you've learned an example, you don't actually need to see it again. And that can lead to a considerably improvement in data efficiency. So I've talked a lot about one potential goal of continual learning, in my view, that I think, I think it's being studied, but potentially not enough. And sort of that's the thing I intend to look more at it. And that is sort of continual learning as a tool to get forward transfers, a tool to learn more efficiently. And the question is, whenever you set these things up, you kind of want to have an understanding of where the efficiency comes from. Where is this kind of composition of efficiency coming from? Like, what would it imply solving this tug of war? And what I want to talk here about is more about like a protocol, an evaluation protocol that might help us get an understanding of what's going on. So what we're thinking about, and what we call sort of this distractor problem, is we have a sequence of tasks, A, B, C, D, and ideally we want to see that you start learning faster. And a question could be, what is a realistic expectation? Like, how do we know if I deploy a system and I'm looking at the speed of learning, so area under the curve for the training error, how do I know that it's doing significantly better than just fine tuning like normal HGD? When do I know I hit some kind of ceiling, and this is the best you could potentially do? So you have all of these questions when you set up a benchmark, right? You want to know how much wiggle room you have to improve, and you want to have an understanding of where this forward transfer could come from. And here we're proposing a very simple thing that I think it's interesting. Maybe it's trivial for many of you, but I think it's interesting. And here we're assuming that one particular problem that continual learning needs to solve is this distractor problem. So if you have a short sequence A, B, C, where A is related to C and B is not related to C, one way to phrase continual learning is you want to be able to learn in such a way that continual learning should mitigate the interference produced by the distractor task B. So you'd want to see that you learn C as efficiently as if you never had the distractor task B in the middle that wasn't that useful for C. And I guess in terms of more, to be more pragmatic, it's always kind of difficult when you talk in sort of abstract terms, is what does it mean in practice? And in particular here, it feels like you need some kind of definition of task similarity, right? When we say A is related to B, but B is not related to C, sorry, A is related to C, but B is not related to C, the question is, what does that mean? And one simple thing, it's maybe not the optimal thing, but one simple thing that you can do is you can look at the transfer matrix, right? You can look at pre-training on any of the 3 tasks and then fine-tuning on a different task. And then you look at this matrix and you can say, well, B is a distractor if I pre-train on A and fine-tune on C, I learn much faster. But if I pre-train on B and fine-tune on C, then I learn slower. And now B becomes a distractor, and now what you can do is you can define a target of what the continual learning system can do. In particular, what you can say is you want the continual learning system to learn C as fast as if it was pre-trained on A, right? So this gives you a number, an actual number that you can have as a target, and now you can run your systems and you can see how does it do compared to that number, how far away you are from that number. And we try to do this. So this is not a supervised task. For whatever reasons, we ended up doing this in RL, but we try to build a sequence like this based on the MetaWorld, which is this very well-known meta-learning benchmark that involves robotic manipulations. And the reason for this is because the tasks are somewhat realistic, so it's not permitted MNIST. So that's sort of what we didn't want to do. We didn't want to do permitted MNIST. So this is a bit more meaningful, but at the same time, it's cheap enough, right? So you can work from the state, so you don't work from the pixels, and that makes the observation relatively small. And you can get, going through 10 of these tasks and learning them to convergence. You can do that in like 3-4 days on like normal hardware without requiring huge clusters.
5 minutes left.
Oh, okay, perfect. So that felt as a good choice for us. And then here again, you can define forward transfer forgetting in the typical way. And as I mentioned before, forward transfer is just the eye under the curve. You can look at the paper for more details, and you can look at the transfer matrix and build this kind of sequences. And you can also get this this target of like what would be the number if you just fine tune. And I think the conclusions of this is, you set up the protocol like this, and then you run existing continual learning algorithms, and what you find is that none of them give you any kind of forward transfer. Actually, all of them, even though they remember these tasks that were before the distractor, they actually work worse than if you just fine tune. And sort of, I think the reason why this is interesting is that it seems that the way we're solving continual learning, we're solving it in a way that it doesn't allow you to get this composition of knowledge, and it doesn't allow you to get this forward transfer. So this is basically the challenge. So I haven't talked at all about the solution. I've mostly talked about the challenge. And I wanted to just a highlight of this paper, I guess just one single slide. I think the other danger, besides the fact that we haven't set up continual learning challenges to measure what we want, is the possibility of these challenges to be too toyish. So in this paper, we do this very simple thing. We rely on this work about mode connectivity, and we look to see what is the connection between a multitask solution and a continual learning solution. And what we find, sorry, I'll just say it in a line. What we find is that these multitask solutions are linearly connected to the solution you've learned on the first task, which basically mean at a high level, what it means is that the multitask solutions that you find, they're all within the region where a second order Taylor expansion holds. And that's sort of the typical assumption that any regularization-based continual learning method does, like a Gaussian approximation of your procedure, or things like this. And you can interpret this in 2 ways. You can interpret this as saying, well, it's okay to make this kind of assumptions, and we should push more on this regularization-based methods, and they should work as well as rehearsal-based methods that typically tend to do better. But you can also interpret this as, our tasks are too simple, or something is wrong with the task that we have, because I can take a simple second-order Taylor expansion of the first problem that I've learned, and I'll have the solutions of all the other tasks that I want to learn within that region. And I think technically, that shouldn't really happen. For complex enough tasks, that shouldn't happen. This again kind of shows another weakness of potentially some of the benchmarks we have. So here we relied on things like permitted MNIST, rotated MNIST, PLCFR, and so forth. And for all of them, this turned out to be true. I just wanted to say it's been like a hard 2 years because of the pandemic and so forth. I just want to thank everyone I worked with. This is just a list of people I worked on several projects in this last couple of years. I'm sure there's a lot more people that I've missed, but at least I've tried to put as many names I could remember down on the slide. And thank you. And if there are questions, I'm happy to take them.
Thank you so much, Razvan, for your great talk. I think it was a very introductory, nice introductory talk, like an opening talk for anyone interested in continual learning. And I also enjoyed a lot of interesting insights, like the one that you said about the efficiency and possibly also this idea of applying continual learning to even, stationary problems, right? That could help. So do we have any questions? I know that we have a bit of delay with respect to the YouTube live. So let's see if we can gather a question in the chat here. Okay, this is interesting, I think, from Subankar Ghosh. He asks, can you please put your view on that the fact, I guess, that bigger networks will try to help to reduce forgetting. So is that the thing? Would bigger networks with more parameters naturally help reduce forgetting?
Yeah, I think this is true. Actually, I don't know of a paper, but I've definitely noticed it myself, and I've seen a lot of people that notice this effect. And in some sense, it's not surprising. Like if you think of in the limit, as the model goes, like if you follow all the works like Belkin's work and so forth on understanding neural nets in sort of these extremes, what happens is that the solution stays very close to initialization. And I guess a toy image that you can have is at some point you don't actually need to learn the intermediary layers. They act as a random projection and you just learn the output layer. And in that sense, it is obvious that forgetting would be less of an issue because you're not actually doing any learning. No part of your model changes or nothing changes too much. Now, the only question is, this is cool, we can observe it, we can exploit it, or we can exploit it for a paper, but can we exploit it for real applications in the sense that, and then this could be a question for deep learning in general. I feel like a lot of things in deep learning rely on overparameterization, but the question is, can we always assume that we will be overparameterized with respect to the complexity of the problem that we learn? And what happens when this is not the case? Yeah, it's not clear to me. Like I think it's useful in the moment. I think there are, even now we can exploit it for some of the tasks we're doing, but as we move forward, at some point, like the same way as random projections, they kind of died out because at some point you can't rely on it, right? You can't be that overparameterized, so then you need to deal with the underparameterized regime. But yeah.
Thanks, Razvan. That's perfect. So if we don't have any more questions, I think it will be like a nice time here now to switch to the next talk from Adis Gunz. So thank you, Razvan, and feel free to join us in the panel session this afternoon for us, but I guess in a few hours. Yes, Razvan, you are in UK, right? So it will be like afternoon. Okay, great. Thanks again.
Thank you.
Yeah, Atis, if you want, you can try to share your screen and let's see if the mic is working as well.
Yes, hello. You can hear me?
Yes, we can. Hi. So thank you, Atis, for joining, and let me introduce you to the rest of the world that is following us on YouTube live and on different platforms. Actually, we are putting this content over. So Atis Gunz is a reader in intelligence and robotics at Cambridge University, where she also leads the Effective Intelligence and Robotics Lab. And I believe that her deep experience and background at the intersection of machine learning, robotics, curriculum learning, effective computing, and AI embodiment can really guide us and inspire us to take a broader view of continual learning and related topics, right? Because it thanks also to this interdisciplinary approach, I think that we can grow as a community. So thank you very much, Adis, for being here, and we're eager to hear your talk.
Thank you very much for inviting me. You can see my screen, if you can just confirm that.
Yep,
yeah.
we can.
Okay, perfect. So I'm actually glad that I'm following Razvan because he already provided the definitions and so on. So I can really focus on the research that we do in my group, which relates to effective computing and effective robotics. So I'd like to start with just first of all, the motivation. So in my team, as was said already, we do a lot of multidisciplinary research, and the main motivation is actually looking at how humans interact between one another. And mainly we focus on non-verbal social signals. As here I am depicting on this visual, we have, when it comes to dyadic interaction, we have a person who is like the source of these signals or the sender of this source of the signals. And we have the receiver end that constantly actually unconsciously or consciously receives these signals and interprets them at different levels. And in these sort of interactions, we actually communicate a lot of things through the way we position ourselves, the way we use the environment, the way we express, the way we gesture. And all of these are interpreted at different levels, for instance, when forming first impressions, or even deciding whether someone is happy or not, or whether we can trust them, and so on. So all of these are quite complex already in human-human interactions. And if we start replacing either the receiving end or even the sending end of these signals with artificial systems, in this case, I'm just depicting a robot, we have many more other challenges. And this is what we're interested in particular. And for effective robotics, what the focus is really to try to interpret and perceive the signals from the users, from the humans, in terms of their nonverbal behavior, affect, personality, and so on, and then try to then interpret and adapt the robot with generating appropriate behavior. So that's really the challenge. And the projects that I'll be talking about from now on relate to these challenges. So the first work I'd like to talk about is where we explored and proposed a theoretical framework for how continual learning can be used for effective robotics. And we explored really these questions of why, what, and how. So why it's needed, what does it mean really in this context, and how we can achieve this. It was presented last year at Roman conference. It's a collaborative work, particularly Nikhil, actually a PhD student working with me, has been driving a lot the continual learning work in our group. And Sinan Kalkan also was a visiting researcher last year in my lab. So we have done a lot of collaborative work together. So in terms of effective robotics, first of all, the motivation is actually they're becoming studied and largely involved in different settings, including healthcare, so how we can deploy them and use them there, but even for services like servicing in restaurants, assisting in elderly care, or even becoming companion at homes for different users and applications. So these actually, all these applications really require the robots to be equipped with these abilities that I mentioned to understand the nonverbal behavior of humans and also try to respond to them appropriately and accordingly. And the main need here is for adaptation. So initially the robots such as Pepper, both from industry, they come with some models that are equipped already. So they have a perception and behavior model out of the box, but then they must learn to interact and adapt with users during these interactions. And they need to also extend and apply this learning with other users and to adapt to different user groups. So this becomes really challenging as the robots learn and adapt to more and more different settings and users. So what is the problem with traditional approaches then, and why do we want to use continual learning for this particular setup? So in terms of traditional approaches, and I can put them side by side here. So basically robot capabilities are really a result of models trained on generic, particularly benchmark data sets. I think Razvan also mentioned this as a problem. And they're okay to try to, because the aim is to generalize. But when we move these approaches and models to actual real world settings, they're not that easily adaptable to different users, different needs, different contextual settings. And continual learning actually enables this incremental learning and integration of knowledge with sequentially made available data. So that's quite useful. And these models are also quite sensitive to changes in the data conditions and distributions, and they can actually adapt to this new information without forgetting. So here I'll try to visualize this theoretical framework we proposed. So we have the robot at the center of this framework. So an effective robot would need to learn how to perceive user behavior, acquiring new instances of data with each interaction in different sort of contexts. So it also needs to learn to interact with other users. In real world situations, the robot not only would need to acquire new instances of training data about a user or a task, but would also need to learn and apply understanding across subjects, learning new conceptual mappings with each user. And continual learning as a paradigm is really well suited for such learning, and effective robots would really benefit from this. Let's look at a more specific example here. So here we are considering a person sort of in a home setting, and the robot needs to perceive and understand the effective behavior of the user in a home scenario, trying to engage with the user. So again, if we put together traditional machine learning approaches and continual learning, so most traditional affect perception approaches are insensitive to the context, as we said, and use a pre-trained perception mechanism that doesn't adapt. They ignore also the nuances of the user in terms of their behavior. But continual learning uses a pre-trained model, so it can use it as a starting point, but then it can evolve with each user as well. So interactions with the user can help gather more data, and then the robot can update its model with each interaction and can try to sort of personalize towards each user. We also highlighted in this paper that this is not straightforward and there are many challenges, and we provided recommendations. I won't be able to cover all of them due to the limitation of time, so I'll just want to cover a few. So gathering person-specific data in this context is a challenge. And I'll explain again why and how we can try to address this. Because person-specific data is limited, so we really learn from interactions, and interactions are really the only source of data for the robot. So to address this, one solution could be to hold some introductory sessions with the robot to enable data collection. We could also perhaps use generative models to simulate additional person-specific data to augment the learning. Another challenge is obtaining ground truth. This is particularly, again, important for affect perception and recognition, where it's more subjective as well, the way people express and interact. And the ground truth indeed varies with users as well as context. So unsupervised learning can potentially be used to mitigate this, but in real life interactions, such adaptation can become a bit intractable. So continual learning, again, could actually provide focus on learning by obtaining some normative baselines. So we can again have some initial interaction rounds with the users, and this could provide baseline, and then the model can learn deviations from this baseline. And also we could perhaps exploit semantic associations, groupings in terms of contextual attributes. For instance, we could group users based on gender, personality, and this could help speed up the learning process. Another one I'd like to talk about is learning without task boundaries. Again, this is important for human nonverbal behavior. Razvan showed some videos of the robot. The same applies for humans. You know, we can't really have segmented or pre-segmented videos when we put these robots into the real world. So you really need to learn actually without task boundaries. So again, if I put here the why and how, so the context might overlap as well, and the robot would have a tough time keeping up with all the changing contextual settings. So one solution here that we propose is the continual learning models can be made context aware by learning context embedding separately, and they can use them also as additional input for the models. And this could help also with smarter context switching. So we cover a lot more in the paper, but here, just as part of this particular paper, in conclusion, we really proposed this theoretical framework, and we showed also with various experiments and formulations how it can be used and applied to effective robotics to enable perpetual evolution of robot capabilities. So the next work I'd like to focus on is learning social appropriateness of robot actions. This was also, again, a work from last year. And currently it's under revision as part of a journal. Again, it's a collaborative work as part of Jonas's master's dissertation in collaboration with Sinan as well. So this relates to social appropriateness of domestic actions. So in the most common sort of works that are similar to this would be particularly for robot social navigation, but these works do not really look at the social appropriateness, and also they do not really investigate domestic actions. So our contributions here are twofold. So we actually create a data set, we call it manners data set, and we provide also labels. And we also propose the usage of a Bayesian continual learning framework for this problem. So appropriate social behavior is not trivial. Here I'm visualizing it in a setting where there are people in sort of living area and there's robot in there. Humans have this natural ability to actually recognize social context, and humans continuously learn from observations as well. It's not very straightforward for the robots, and that's the reason we undertook this work. Again, we have motivation from multiple disciplines, particularly from social sciences, this use of space in social interactions. So Adam Camden's work has been quite influential for this. Here you're seeing, for instance, how space has been actually modeled as a conceptual lens to analyze interactions. And we have these concentric zones around each individual for different kinds of interactions. So for instance, when we look at the really intimate zone, this 0.5 meter, only few people we would allow into this zone, only very close people could be actually in this space. And as it moves away, then we could have different interactions. Also, Adam Camden's characterization of this F formation system of spatial organization was also quite useful as a conceptual lens to analyze social interactions. This has been used already for vision-based analysis of groups and standing group conversations and so on. So we draw motivation and inspiration from these. And then we create this synthetic data set with various features that you can see on the table on the left. And you also have this visualization of what sort of aspects we have in the data set. So we could actually position the robot in different settings. We can decide on number of humans, children, animal, number of groups, whether the robot is facing the group, how far is the robot to the closest human, and so on. So we really chose to go with the synthetic data set because this sort of variation is very difficult to obtain in the real world with actual humans and animals and robots and so on. So here's one example of a scene where we also have this arrow of directionality of the robot action. Some people are standing, moving, some are seated. We also have this, whether music is playing, whether there is an animal there or children, as you see here depicted as well. This dataset was created in Unity, and along 29 features was varied. It's 1,000 images with 16 robot actions, and it was actually labeled via crowdsourcing. We obtained 15 judgments for each of these scenes. Here are the robot actions. So there are 8 different types within a circle or in the direction of an arrow. These include typical domestic actions like cleaning, carrying food, or starting a conversation, carrying objects, mopping, and so on. The annotation was conducted in this way online. So the people see a visual scene and they're asked to provide on a Likert scale how appropriate they think each of these actions would be. We also asked them to provide a reason for this. We did a lot of analysis. I won't be covering all of them, but here I just want to show some interesting results that also contribute to our understanding of this sort of social appropriateness of domestic actions. So for instance, here we see for different actions, as I said, we take into account this use of space. We can see here how certain actions are appropriate when the robot is very close to the human. So for instance, what would be really inappropriate is if the robot is very close to the human, they shouldn't be carrying big objects or mopping the floor, but starting a conversation is really appropriate. And as the robot moves away from the person, starting the conversation would become gradually inappropriate. Here is another analysis, appropriateness with respect to orientation. Here we are looking at how humans and robots would face one another or would deviate from facing each other. And depending on this different configuration, how the appropriateness values change. Again, you see, for instance, here starting a conversation is perceived as not so appropriate if they're not facing one another. But interestingly, if the human is behind the robot, it's actually perceived as appropriate. But if the robot is behind the person, it's not perceived as or labeled as appropriate. And we can see different variations also for the other actions, for instance. So, carrying big objects, for instance, becomes less appropriate when human and robot are facing one another and so on. So these are really insightful findings. Here we also see a visual example, an extreme case where the robot is alone. In this case, the actual label, this is the average of judgments. We see how most of the actions are seen as appropriate. Some are more appropriate than the others, but because there's no one in terms of human or animal or children in the scene, these are perceived mostly as appropriate. As the next step, we do continual learning. So we use a Bayesian neural network as baseline, and then we look at as 2-task or 16-task model. So the 2-task refers to first 8 actions within a circle and the next 8 actions within the arrow, or the 16-task would basically gradually take each of these actions I specified. Here I'm showing results for the 16-task model. So it's divided into 2 to make it a bit more visible, starting from task 1. So here we're plotting the loss on each action as root mean square error between the predicted appropriateness and how the model learns on that task and action. We see that the loss drops for that action, and then it stays low throughout the process, meaning that the model is actually able to mitigate the catastrophic forgetting. We also see that, on average, we have this average root mean square error of 0.63 for all the tasks, which is actually quite satisfactory considering we have a scale from 1 to 5. Here are some testing examples. So for this scene where the robot was alone, we see what the actual label is and what the models actually predicted. Again, you see the predictions are quite close. Some are better than the others. And another example where we have humans. In this case, obviously, some of the tasks are seen as inappropriate, such as vacuum cleaning, and the models are able to capture this appropriately. Okay, so in terms of this part of the work, in conclusion, basically, we looked actually at this from a third-person perspective. Here, I'm just showing, like for NASA Mars rover, how a third-person perspective would look like for the robot. But of course, when robots interact, they need to have their first vision, so robotic perspective to the world. So this is a challenge and an open question for analyzing this sort of actions. So this is probably a future work to look at. Okay, the next thing I'll cover is now sort of shifting a bit from all of this towards bias, and particularly looking at bias in facial expression and action unit recognition, and how we also propose to employ continual learning for this. But first of all, I'll provide a bit of background work before we look at the continual learning approaches. So we had a couple of works on this last year. Again, this was as part of ECCV workshop investigating bias and fairness in facial expression recognition. Again, it's a collaborative work. Bias in vision-based AI models is by now quite well known, so I won't go into too much detail, but basically dataset bias refers to the fact that, we might not have an even distribution of data for the subject in terms of demographic attributes. And algorithmic bias would mean, actually, for instance, for deep learning, pruning and quantizing these networks sometimes is found to amplify algorithmic bias. Here's one example quite commonly known, for instance, how for gender classification from 2018 work, it has been found that with the color of skin changing, actually the error rate is significantly changing as well, really showing this bias. And the same was found also for like applications in terms of prediction of personality. Here you see just changing the brightness impacts the prediction, or wearing glasses impacts the prediction, and so on. So for us, fairness in terms of expression recognition, what we wanted to investigate was, first of all, we have a baseline approach, which is an 18 layer ResNet, commonly used for visual recognition problems, and it's relatively lightweight. So we train an expression classifier with cross entropy loss for this. Then we also have these 12 other approaches. The first one is fairness through awareness. Here we investigate how explicitly providing the sensitive attribute information can affect the expression recognition, and we are focusing here on gender, race, and age. And we use the one hot attribute labels are concatenated and upsampled through a fully connected layer, and the size of this upsampled representation then matches the size of the ResNet extracted features, and from there we try to learn the expression classification. The next one, fairness through unawareness, is also known as the disentangled approach. We investigate here how explicitly dispelling these attribute information can affect the expression recognition. There's a primary branch designed for expression classification, as you see, but there are also several parallel branches there. And each branch contains two parts. The confusion part tries to estimate equal probability for each sensitive attribute. And also we have the classification part that learns to predict each sensitive attribute correctly to prevent the network learning a trivial mapping solution. So we did various experiments, but particularly I'm going to just present on RAFDB data set because I'll use the same for continual learning experiments as well. So this is like an in-the-wild data set of faces with various expressions, 6 particular facial expression categories here. And then we have also neutral as well. In terms of gender, there are male and female labels. In terms of race, there are 3 groups. And in terms of age, there are these different 5 categories. Then the next step is also to do data augmentation, which is very common for computer vision tasks. We combined some of these techniques together, so cropping, rotating, mirroring, histogram equalization. And in terms of evaluation metrics, we did employ the typical accuracy, which is very well known. So it's the fraction of the predictions that the model predicted correctly. But then for bias and fairness, we employed a specific metric. So fairness should indicate whether a classifier is fair to the sensitive attributes. And there are different measures, I have to note, but we employed this equal opportunity. And here the idea is that the classifier should provide similar results across different demographic groups. So then we are comparing basically, fairness here is defined basically in terms of this largest accuracy gap among all demographic groups. So the first thing to look at in our experiments is what is going on in terms of data sets. So here you see the distribution along the sensitive attributes, the number of samples available. So the data set is indeed biased. And then we see results here in terms of accuracy. We see that augmentation actually helps in terms of accuracy. And then particularly the disentangled approach provides better results in terms of accuracy. So let's look at now in terms of fairness values. So here what we see is if the distribution of the groups are more or less even, the effect actually is mild. So for instance, for gender, again, we see with disentangled that attribute-aware approaches provide best results, but the effect is mild. But overall, we see here that disentangled approach is really the best one for mitigating demographic bias. So the next thing we wanted to look at was actually towards fair effective robotics and using continual learning for mitigating bias. And the motivation from this comes from HRI and robotics research, where even those studies with robots found actually biases and prejudice, but there are not many solutions proposed, particularly at the algorithmic level. And there are different methods for bias mitigation. Here I'm showing a taxonomy. So our research question was, well, can we actually employ continual learning? Again, I don't need to convince you by now because we already mentioned why continual learning could help, but particularly for bias, it has the potential for robustness against biased attributes and also balancing learning across different domains. So hopefully that would lead to developing fairer models. So what we do here is we focus on domain incremental learnings, which means the task here is the same. For instance, for expression recognition is classifying facial expressions. And then we have in terms of attribute the gender, therefore our domains would be male and female. And then each split would have samples from one domain. And then the model basically is trained one split at a time and learns incrementally. We compare non-CL based approaches versus CL based approaches. And I won't go too much into detail about this. If you have questions, you can ask because I'm also conscious of time. But basically, we have the baseline. Here we train the model under domain incremental settings, but without applying continual learning. Then we have the offline model. Here, all the data is used for training the model from scratch. Then we have the domain discriminative, where we have N is the domain and M are the number of classes. Then we have this domain independent classifier, where we have a multi-head structure. Each head corresponds to one of the domains. The disentangled approach I already introduced previously, so we are comparing to that as well. And finally, strategic sampling, it adds a loss weight for each domain inverse proportional to the frequency of that domain. And in terms of CL-based approaches, we employed quite a few, but we primarily explored the regularization-based approaches. This was to have a fair comparison with the non-CL approaches because they do not require extra capacity like generative models. But we employed these four, and plus we also implemented a naive rehearsal strategy. The fairness measure is more or less the same, so I'm not going to probably go through in details, but we're also visualizing here with the green and blue to really show what fairness would mean in this particular case of race. So we are in this paper, we are really trying to improve the fairness measure overall. In terms of experimental setup,
5 minutes left.
Sorry?
5 minutes left.
Oh, okay, 5 minutes, so I don't have to rush. Okay, but I'm coming to an end anyway. So we are looking at 2 data sets for expression classification RAFDB and for action unit BP4D. And we are using the same sort of ResNet-based CNN architecture for all the models. And we run the experiments 3 times and average the results. So here is the one for expression recognition with RAFDB. So here the task is to learn these 7 categories. So here we see that particularly the synaptic intelligence provides the best results, and overall the continual learning methods provide better results in terms of fairness. And if you look at the facial AU detection, this is a more complex problem because the multi-label detection and classification problem. Here we see for gender, the disentangled approach is best, but for if you look at further down, we see actually the naive rehearsal is good for race. We explore these variations and differences also in the paper, so I won't cover too much in detail, but what I want to sort of conclude is in this work, we proposed the novel usage of continual learning for developing fairer models, in particular for facial expression and action unit detection. And we also highlighted how they can help mitigate the bias. So they can really balance learning across different domains. And most overall, they outperform the non-CL-based approaches with respect to the fairness metric utilized. But in the paper, we also cover accuracy-related aspects as well. As future work, we want to focus on incorporating these to long-term HRI studies. So if you're interested, we actually had a workshop as part of HRI on lifelong learning and personalization and long-term human-robot interaction. So the video is available just like this workshop. Also, we have a special issue research topic on frontiers, on lifelong learning and long-term human-robot interaction, covering some of these aspects with different articles. Some of them are already out. And I just would like to thank the team over the years that has been working with me and also the funders. Thank you very much.
Thank you, Addis, for this great talk with a lot of insights and different works that you have carried out on the topic. So that's great to see. So let's see if we have some questions from the audience. Again, we have a kind of 40 seconds, 1 minute delay with respect to YouTube. So they're gonna start rolling in a few seconds. But in the meanwhile, I can start by reading the question, from Matthias, I think, directly on the discuss chat on our website. And he says, continual learning is of great importance to apply robotics in the real world. But many other components like open world learning and out of distribution detection seem to be needed. What is your view on the missing components and how far have they progressed? And following on this, when do you see human-robot interaction being indispensable in society? Wow, that's a nice question.
Okay, so I think, I mean, these are difficult questions in the sense that when we will achieve, I always get this question also, when we will have the robots in our homes, when the robot can do my ironing.
Yeah, that would be great.
Yeah, so I think this is difficult to predict, I have to say. So I cannot say in 5 years' time we'll do this, because even researchers before me tried to make predictions and it didn't always come, true. So I always actually refrain myself from making such predictions. Regarding the first part of the question, I agree there are many missing components. And not only in terms of the ones he mentioned, but even in terms of, most of the time what happens is the perception aspect of robots are investigated separately from the rest of the components. So in terms of, actually making decisions and then creating behavior based on that, having the full loop is not always studied together. This is the main problem, I would say. Even in terms of like a conference like CVPR, very good for object detection and so on, but most of the time, the algorithms are actually investigated specifically what I would say on the perception side. So having the full loop, particularly in HRI, the full loop close together and investigated together is the main problem. It's not done. And here what I presented also, as you saw, touches upon different aspects, but again, not the full loop of it. And that's the main challenge, I think, because we just tackle different aspects, different modules. And when we try to bring it together, obviously it doesn't work. It doesn't go smoothly because we are not trying to optimize the problem together. That's what I would say.
Absolutely agree. And so we have a follow-up question. So machine learning is slowly making its way into the robotics community, right? However, it's often difficult to to deploy pure machine learning solutions to real-world robotics system. And continual learning approaches are even more unstable and arrive, I would add. Do you think it is realistic at this stage to see continual learning applied to real-world problems in robotics?
So I didn't cover all the challenges as I was talking about the theoretical framework. Indeed, another challenge we mentioned was actually the robot hardware and software. When we run some studies, even just in the lab, we can tell even just from the in-lab studies, most of the robots are quite limited, and no offense, of course, to the producers of the robots. But when they come with certain onboard capabilities, they're most limited, even in terms of, the camera they have. To really do facial action unit detection is not really most of the time sufficient what they're equipped with. So we were saying most possibly trying to, or even storage and the hardware to run all of these algorithms to do real-time training on board, it's quite difficult. So one thing would be to try to employ cloud robotics to try to sort of, put it together by using cloud, but also more recently, one of my students started working on federated learning. That probably is the way forward. So we do not rely on a single sort of, board to learn and simultaneously adapt and so on, but we actually sort of offload some of the aspects to the cloud while also envisaging sort of multiple robots learning simultaneously, perhaps the different aspects, but sort of combining what they learned and their experience over a single model so that the robots can update this way. So that probably would be the next thing.
That's great. And I hope to see more effort trying to work towards solution, putting together robotics, federated learning, and continual learning maybe, because they are somehow complementary. So thanks again, Atis, for your great talk again and for being with us. And we are incredibly in time for the next talk now with Joost van de Weijer. So I want to call on stage actually Pau Rodriguez, who is going to handle, let's say, who's going to chair the following sessions. Actually, no, I think just the follow-up session with Joost. So hi, Pau, are you here? Okay, I can see you, I can hear you. So I'll let you introduce Joost. Bye.
So I'm pleased to introduce Joost van de Weijer. He's a research leader in the machine learning perception team and a senior researcher at the Computer Vision Center in Barcelona, where I did my PhD. And I think he's one of the most brilliant researchers we have in Spain. And you can start your talk. I don't see you. Okay.
Thank you, Pau. Can you see my screen?
Yeah.
Okay, thank you for the introduction. I will talk today about exemplar-free class incremental learning. And we'll present two works we did here in the Learning and Machine Perception group in Barcelona. I will focus on exemplar-free incremental learning, so meaning that you're not allowed to have access to any data of previous tasks. So just as a quick remind, incremental learning, we are learning multiple tasks. So here, for example, we are learning first dogs, then, let's see if this works. Yeah, first dogs, then cats, then birds. And we want to learn them in a sequential fashion. And after learning the third task, we hope we can still perform well on the previous tasks. So a naive solution here, for example, fine-tuning, would result in catastrophic forgetting. So we would only be good in the last task and forget the previous ones. And just to remind you also, let's say the upper bound, the goal of incremental learning is maybe to reach as close as possible to joint training, where we train jointly on all the 3 data sets. And we are far from that at the moment, actually. One big distinction there is in the community, I think Vincenzo already mentioned, so that between task IL and class IL. And in task IL, when you're learning a sequence of tasks, at inference time, you get the task ID. So you know your sample comes from a certain task. For example, what label is this sample? And it is from task 1 you have to solve. So you only have to pick it's a circle or a square in that case. In class IL, the problem is more difficult. You have to classify samples coming in at inference time, coming from all classes you have seen during training of all the tasks. And this not having access to the task ID make this a more difficult problem. And Vincenzo also mentioned, so class IL is getting more and more traction. I think it has been true mainly that in computer vision, class IL is growing rapidly. I think in machine learning, task IL is still an important part of the research. And in the end of this talk, I will actually reflect on this and think that task IL also needs still much work, and which can be very beneficial for class IL. We have done in the group a recent survey on class incremental learning, in which we compared 13 state-of-the-art methods and baselines. Here is an overview of the methods we considered. And we have published the code, which allows you to reproduce all the results on Cypher, which we have in the survey, and compare your own method against all these methods. And here's the GitHub page. So one approach to address catastrophic forgetting in these networks is by taking a memory buffer. And that allows you to use samples from previous tasks. And this works very efficiently. But in this talk, I want to focus on exemplar-free incremental learning. So you are not allowed to store any data from previous tasks. I think this is an increasingly important topic, especially for applications where data privacy and security are important. And in healthcare applications, as well as mobile applications, often it's not allowed to take any of the user's data. I want to say that it's much more difficult than task incremental learning. And as an example, I give one table from our survey, and we compare a set of exemplar-free methods here: fine-tuning, learning without forgetting, elastic weight consolidation, etc., mass here, learning without memorizing. And they get certain scores on a 10-task Cypher experiment. And in general, if you add 2,000 exemplars in total, then you see that the results jump up a lot. So this jumps up from very little in the case of LWF, but mostly 100% for EWC, almost 100 for LWM. It's very nice to have exemplars. So exemplar-free incremental learning is much more difficult, and exemplar-free incremental learning methods should be compared to exemplar-free incremental learning methods, baselines, and not with exemplar-based methods, because they are much better. It's a more strict setup. And exemplar-free methods were for a while more popular in task IL, but when moving to class incremental learning in computer vision, the majority of the methods started using exemplars. So I will talk about two main works here: semantic drift compensation, for example, of free incremental learning. And the second work is pseudo feature replay, also for example of free incremental learning. And finally, I will talk a bit about challenges in incremental learning and some recent work we did. So first, semantic drift compensation. So most of the work in incremental learning is done with classification networks. So you have you're learning a first task, for example, classifying dogs. You have a classification network and it outputs a probability over the classes. So then when I start learning task 2, I add a new head to the classifier because now I have to classify more classes, also the classes which are new in task 2. And I will output probability over all the classes seen up till now, so including the ones in task 1. So another way to go about this problem would be maybe to use an embedding network. So in this case, you would learn task 1, dogs again, but now you would try to learn an embedding space in which similar dogs are mapped together and dissimilar dogs are mapped far away in this embedding space. You could do this, for example, with any metric learning loss. So the triplet loss is used by us here. And when you want to do classification, you could, for example, do nearest class mean. So you keep the mean class representation. You could call this, for example, a prototype. And then at testing time, when you have to classify an item, you look what is the nearest class mean and classify it as that label. The nice thing is that if you add another task and you learn this embedding network, you do not have to add any new weights. So you do have to learn the network to, again, map similar classes together, images from similar classes together from dissimilar classes far away. But you do not have to add new weights, as is the case in classification networks, where you have to add new weights to your head. And these new weights might actually be partially responsible for some forgetting because they need to be learned from scratch. In an embedding network, let's say if you're lucky and the learned network is already good enough in separating the new classes in task 2, you do not have to do anything. So we looked at these embedding networks and how they did on continual learning. Here we do 4 tasks on a flower data set. And we compare it with classification networks. So I will be focusing on the blue and red line, and the blue line is the classification network. And the red line here is the accuracy over multiple tasks, average accuracy over multiple tasks when training this embedding network. And you see that these embedding networks, this is trained with fine-tuning in both cases, do suffer from much less forgetting than the one here, the blue line, which is based on a classification network. So that's already a much nicer starting point for your system. Another point is that you can easily extend existing theory from regularization methods to these embedding networks. We call that EWC, so for E for embedding here, the EMAS, ELWF, for example, and further improve these results. That's something we will do. But when here we see it for several data sets, for birds data sets, the gain is not so big as for flowers, but still significant. And for an action data set, also big gains can be observed. So we're looking, when training these embedding spaces, can we do something more than just adding existing methods? And consider this case where we are classifying 2 classes of flowers, the sunflower and the daisies here. And our network has managed to map them together. The sunflowers are here, the daisies are in this part of the embedding space. And now we start learning 2 new classes. It's crocuses and lilies. And at the start of training task 2, these might not be centered yet. So we have to learn the embedding space in such a way that all these new orange dots are close together and the new purple ones as well. Now let's say we do that and we manage to map them all together, the new class, the 2 new classes. And while doing this, we are not revisiting data from the previous task. So since the feature extractor will be changing during this training, now the data of the old task has moved in space. Let's say We see here a vague position of where it used to be, but it has now moved to a new position. Now, the drift which you observe of, let's say, this arrow is in the wrong direction, I see. Let's consider this one. The drift you consider from the original location of the class, the prototype class after training task 1, to the new location of the prototype after training task 2. We call this the semantic drift vector. And if we would be able to measure this semantic drift vector, we can compensate for it and probably do better at classifying images. So if you have data of previous tasks, that would be easy, no? Because you can just run it and you can compute your new mean and get your drift. But okay, we want to do this without any access to previous data. So what do we propose to do? We have learned task 1. Here are the dots and the prototypes are a little bit bigger. Now we have the data of task 2 and we want to start clustering this data in the classes of task 2. And while doing so, we can observe the drift of this new data. So this is what we can observe. And from this observed drift, we somehow want to be able to estimate the drift of the prototypes of previous tasks. So how does the prototype of this task move during the training of task 2? So we have some known drift here, which we can actually observe. These vectors we observe, and we have an unknown drift because we have no access to this data anymore. But we would like to estimate these semantic drifts of the prototypes of previous tasks. So we proposed a method which looks at the known drift and sees this as forming a vector field in the embedding space. And what we want to do is estimate the vector which happens at the previous prototype. And what do? We interpolate between the vectors in a local region around the previous prototypes. So we use a Gaussian window here, and we take the average of the vectors within this Gaussian window. So let's say for this prototype, we consider these 3 observed vectors, and we average this according to the distance to the prototype, and we get an estimate of the drift of this prototype of the previous task. If we have this estimate, we can now compensate it for it and hopefully improve the classification of previous classes. So does this really work like this? We did a simple example in the 2D embedding space for MNIST. After training the first task, we have here the 5 classes of the first tasks, and they are nicely separated. The data of the second task is all over the embedding space at the start of training the second task. But now, while training the second task, it's also starting to cluster. But it starts to, let's say, decluster the data of the first class. And what you see here is that the purple data, which originally was here, now moved to this position. And we can see that the new prototype position is here, and our SDC estimate is to put it here. So you see that it improves. It overshoots in this case, but for example, for the blue case, it's spot on. And yes, you could say that, okay, the method works to some extent and manages to estimate this semantic drift. So after trying it on MNIST, we also explored some more complex data sets, flowers, birds, and actions. Here is some results. We compare several methods: fine-tuning, learning without forgetting, elastic weight consolidation, and mass. And this is without semantic drift compensation. And you see that the average after 2 tasks is reported here. After semantic drift compensation, we see significant gains. So for example, for fine-tuning, it goes up from 56 to 62. And mass goes up a lot, actually from 65 to 84. It jumps almost 20%. So you see that this semantic drift compensation can help you while using these regularization methods on embedding spaces. So that was the main observation from this table, I think. Here we do 4 tasks on birds. This is a classification network with fine-tuning. So you see 18 accuracy, average accuracy after 4 tasks. If you use embedding network and fine-tuning, you already more than double that, 38.7. And if you use the semantic drift compensation, you jump another almost 10% up. If you combine it with LWF, you get a more moderate jump of only 3%. EWC here, you see also another jump of 5%. So in general, yes, this semantic drift compensation can be used to improve your results. We tried this on all data sets and found similar conclusions. So SDC manages to improve all these methods on all the data set, especially for the fine-tuning baseline. And the gain for EWC and MAS is larger than for LWF. So LWF explicitly tries to reduce the drift in the embedding space. And that's why in that case, the gain is much smaller. So here, for example, I see only a 0.2 gain for actions. No, 1.5 gain for flowers. We also measured if the compensated mean was actually closer to the test data than the original mean. So here, every dot in this plot is a data point of the test data. The 3 different colors is data from the 3 different tasks. So task 1, task 2, task 3. And this is the distance to the original mean and the distance to the compensated mean. And if we are in this upper triangle, we are closer to the compensated mean, and here closer to the original mean. And you see that for most points, the compensation helps it to get closer to the compensated mean. So the compensated mean better represents the data of the class than the original mean. The original mean, I mean the mean which was computed when the class was first encountered. So here we have proposed a method to do class incremental learning without any exemplars. We propose to approximate the semantic drift and compensate for it at test time. I think this is a nice alternative. So most methods focus on trying to prevent forgetting. Here you kind of say, okay, we will have some drift, there will be some forgetting, but if we can measure it, maybe we can still compensate for it. Experiments show that it can lead to significant gains, especially for the fine-tuning baseline, but also when combined with regularization methods. And I think it's interesting to observe that embedding networks already intrinsically are less sensitive to catastrophic forgetting than classification networks. So this cross-entropy loss seems to be partially responsible for this large drops in performance we saw, and which is called catastrophic forgetting. And this something similar has been observed also in 2 other papers, in this continual prototype evolution paper, which is on arXiv, and in the energy-based models, which will be presented today also in the workshop, also show this, that cross-entropy could be partially responsible for the forgetting. So as a second work, I want to talk about pseudo feature replay for incremental learning. So we saw that replay is ideal. It really gives you a significant boost in performance. In exemplar 3 methods do not have access to this, but could we do something? So early on, people came up with the idea, now why not learn again on the first task and then replay the images of the first task while training the second task. So that is a great idea, I think, but for many tasks, I think it's still hard to train again. So these are often very heavy networks, and for the more complex data, their results are still maybe not sufficient, especially when data sets are small. So we were thinking, can we do something maybe less complex than image generation, but still with similar effect. So here we show image generation. So let's say we are training a feature extractor and classifier. We get some data of a current task, which we want to learn. And while doing that, we could be playing again, which generates data from previous tasks. No? So this was originally proposed here in this paper by Shin in NeurIPS 2017. But okay, that's often difficult because training of complex image generation, it's not a solved problem yet. So instead we proposed, why not generate intermediate representations? That might be easier. So let's say here in this case, we generate the feature representation, and then we could still jointly learn this classifier with feature representations from previous classes and with features from current classes coming up. So one problem would be that this feature extractor will have drift during the training. And to prevent this drift to some extent, we introduce a distillation loss. So this tries to keep the output of this feature extractor to be as close as possible to the output of the previous feature extractor. So preventing drift of the feature extractor. So how does the whole system work? Now we have to first just learn our first task, feature extractor and classifier. Then we fix the feature extractor, and then we train again, which gets the features extracted from the feature extractor and tries to generate similar features as the ones extracted with the feature extractor for the classes of previous tasks. Then, if we have this again, we can now use it during the training of the new task. So the new task has some new class images. The new network will be initiated with the previous one. We will have the distillation loss to make the feature extractor not go too far away. And while training with the new data, we will be generating the features from the previous data. And one great benefit for this is that most of these exemplar-based methods, they suffer from imbalance in the data. So you have a lot of new data and only a few samples of old data, and you get problems with imbalanced training. The nice thing is if you have a generator, you can really generate as many old samples if you want, so you don't have this problem per se. An alternative to training again is training just estimating the feature distribution with the Gaussian, with a mean and a variance matrix. We also do that as an additional feature generation model. So then at training time of the new task, we can just generate features by sampling from these Gaussian distributions. So here are some results on Cypher 100 for 4 tasks. Here are some regularization methods. So these are all exemplar-free methods. Image replay fails. So here it gets 18.6. So it has difficulties to generate really Cypher 100 images. Using the Gaussian model, which I explained in the previous slide, you jump to 37% accuracy here. And using again, you can further improve to 41. So which layer should you replay? Here we go through different layers of a network. Could be after convolution 1, block 1, etc. We found that actually just before the classifier gave us the best results. Block 3 is an alternative, which also still gets decent results. But okay, the later the better in this case. How about the overhead? So storing exemplars is costly, so it will have cost in your memory. So for example, storing 2000 exemplars from Cypher 100 is about 25 megabytes of memory. Of the birds data set, it goes up to almost 400 megabytes. Whereas this GAN is only 4.5 megabyte size. So it's a small network you need. So I quickly showed here that pseudo feature replay could be a good alternative if image replay is not yet possible. And it can lead to balanced classifiers and competitive results in exemplar-free incremental learning. So finally, I wanted to talk a bit about, is it really all about forgetting in class incremental learning? So most of the papers start that fine-tuning will lead to forgetting, and this is the main problem we have to solve. Before going into this, I want to have one note that this forgetting was initially defined for task incremental learning. But if you go to class incremental learning, you have to be careful. So in that case, you have to look at the cumulative accuracy, and you have to look at the forgetting of the cumulative accuracy. Something not all people did, including myself in previous papers. So maybe this slide helps to explain what I mean. Often we see these plots here, which is the blue line, which shows your performance of a network while training on multiple tasks, so performance after task 1 is 82, task 2 it's 50, and it goes on, gets a little bit worse, and then at some moment maybe it stabilizes. And here in the dotted line, I've plotted the cumulative accuracy of task 1 in this case. So you see there is forgetting here. The performance, well, after training task 2, the performance of task 1 went down. There is forgetting. It goes down further, but then it kind of stays almost equal till the end. If we look at this point shows the cumulative accuracy of task 1 and 2. So you have to classify all the classes in task 1 and 2. And we can also follow that while training new tasks. And actually we see that this never goes really down. It goes up actually a little bit. There is no forgetting for this cumulative task. The same you can see for here and here. So in general, I think that current class incremental learning systems don't suffer so much as we might think from forgetting. We see it here for task 1, but not so much for the other ones. So that made us think what might be other problems we suffer from. So we are thinking about the difference between class AL and task AL. So in task AL, you have to only distinguish between the classes within a task. So let's consider a synthetic example here. You have to distinguish red diamonds from green diamonds. And we see here that, okay, by just learning this classifier between red and green, you manage to do this task. Now, if the second task is red triangles from green triangles, this same classifier actually pretty much does the job. No? You don't need to learn much more. If you do class AL, you have a much more difficult task because now suddenly you also have to distinguish red triangles from red diamonds. No? So you have to learn, let's say, features which allow you to distinguish between these two classes. For task AL, that's not necessary. So the features which distinguish between tasks, we call them cross-task features, and the features which are important to distinguish between features within a task, we call intra-task features. And we were thinking maybe the main challenge of class AL is actually how to compute these cross-task features, because you actually have little or no access to previous data, and that's a very difficult task. No? So could we get some grip on how important these are? And we designed a basic experiment which gives us some insight into that. We use, in this case, exemplars. We do use a simple classification network, and we train it with a standard cross-entropy loss. So this cross-entropy loss tries to distinguish between all the classes seen until the current task. And it's continually learning new tasks. And we call this method fine-tuning, balanced plus cross-task features. So it tries to really distinguish between the different tasks. We also designed another loss which doesn't try to distinguish classes which are not in the same task. So it tries to only distinguish between the classes within the same task. It's easier, and we call this one fine-tuning balanced without cross-task features. So this method will not be focused on learning cross-task features. So it will learn intra-task features only. Since we want to evaluate them for class incremental learning, in the second task, we freeze the feature extractor and we fine-tune it on the memory buffer, so which has a balanced representation of all the classes seen until now. And we do this in both cases with the cross-entropy loss. So the final classifier tries to distinguish between all the classes, but it does so based on a feature extractor which learns cross-task features and a feature extractor which doesn't learn cross-task features. So then when evaluating this, we saw something what kind of surprised us. So the method which didn't learn cross-task features, here in orange, did worse than the one which did learn cross-task features. But the difference wasn't that big. If we would give infinite memory to the methods, then the method which didn't learn any cross-task features did much better than our current state-of-the-art method, which does use cross-task width. And the upper bound, which also used infinite memory, did even better. So you could say that the difference between the blue line here and the yellow line here is, let's say, the maximum you can get by learning cross-task features. But currently we are here. So of this whole gain, which we still want to get as a community, a part is due to cross-task features, but a part actually seems to be common with task incremental learning. So interesting here is, I think, that progress in task incremental learning would mean progress in class incremental learning. So this gap here can be obtained by learning a feature extractor which only tries to learn intra-task features. So we have summarized these results here, actually for 2 settings, for 10 tasks and 20 tasks. If you go to more tasks, actually the cross-task features become more important. We see here the cross-task features part is in yellow. These are our baseline methods, which use 20 exemplars. You see that cross-task features, the gain by cross-task features is decent. But there is this whole part which is not due to cross-task features. And we also don't believe it's due to forgetting. So we think it's more to do with better knowledge transfer backward, forward between while training new tasks. So these conclusions based on this baseline method, do they hold for other methods? We compared our method, this baseline method here, ftpol, with existing methods, and we found that it actually on Cypher obtained similar results. So we do think that similar things hold for the state of the art, so EAIL, BIC, Lucier, etc. So these methods can gain still some part by learning more cross-task features, but there is still a whole gap which I think we don't understand very well where to get it from. So maybe there is too much focus on forgetting in the community, and we should look into other problems which occur in continual learning. I think Pascanu also referred to this. Task IL, so in this discussion, should we leave task IL? Class IL is more difficult. I think I would be against that. So task IL is actually easier to formally frame. And if we get more progress in task IL, this probably will translate to progress in class IL as well. So I think there is still much room improving that. And other conclusions are that incremental metric learning suffer much less from forgetting than when training with a cross entropy loss. So even when just training with fine tuning, incremental metric learning obtains, I would say, much more decent results. Semantic drift compensation can be used to improve your results if you apply any method in incremental metric learning. And I think also pseudo feature replay is an efficient approach to prevent forgetting of previous classes if you're not allowed to reverse saved exemplars. And it allows you to circumvent the imbalance problem. So I want to acknowledge mainly the PhD students responsible for this work. So Lou, Chailei, Mark, Albin, and the other people on this list as well. And that's the end. So thank you for your attention. I'm happy to take any questions.
And just a very interesting talk. I think really that the last part is very insightful, and it generated some questions in YouTube. So I'll go by order. The first one is from Sai Subramaniam. And the question is, how close should the feature activations of T-1 and T be in order for distillation to not fail? It is dependent on the nature of data across T-1 and T.
Yeah, I think that's an important question. For this is related with pseudo feature replay. And in that case, what happens is that the replay is happiest with a feature extractor which doesn't move. So you will see that depending on let's say how good your representation is during the first tasks, how successful this method is. So I think all exemplar-free methods at the moment they will suffer from very challenging settings where you start with a very small task, for example, and you still have a lot of learning even from the bottom layers. So what we saw in follow-up works is that that the deeper you go, you replay, the quicker you can start freezing this part. So maybe the first 3 layers are well learned after the first 2 tasks, the first 4 layers after the first 5 tasks, etc. So indeed, I would say it depends mainly on the size of your task. So can you learn a good representation already on your first task? Then you want to have very little drift. If you still need to learn a lot, you have to allow for more drift in the first task, and this will certainly lead to a drop in your performance and some forgetting of these classes in the first task. I think.
Thank you. Then we have time for one more question, and then we'll start with the poster session. It's from Herman Blom. He asks in YouTube, does pseudo feature replay also work in a continuous way? Can you also learn the gun continuously?
Yeah, also a good question. Training GANs in a continuous way, you have to do that in this work. I actually skipped that slide for time reasons. In principle, continual training of generative models is much easier than discriminative models because you can generate the data of your previous task. So even a naive approach where you train a generator on the first task, then use it to generate the data of the first task while training the second task and train a new generator with this joint data actually works pretty well. So there are some works, we address this in this work in memory replay GANs, but also there's earlier work from NeurIPS 2017, which I cite in the slide. Yeah, so that's important to do, and it's actually not so difficult, I would say.
Well, thanks. If you want, you can go later to the YouTube channel and you have more questions there.
Okay, sure, I will do that.
So that's it with this last talk. I think you can stop sharing your screen. And now Vincenzo will go over the poster session, explain how it works. Vincenzo, are you here?
Yes, I am. Thanks, Pau. And well, it's rather easy. You should have already seen the instructions to join the poster sessions on our official website. You can go there, and in the landing page, you'll see the instructions. But essentially, you have to go over the Eventbrite event and get a ticket, a free ticket. And there you'll see all the links, all the different to the different Microsoft Teams rooms where you can interact directly with the authors of the different accepted papers. So if you have not already done so, you can just go over Eventbrite. I will just point the link on the chat for convenience. Oh, well, not on the chat, but on the live stream on YouTube. And you can get the links there. This is because we didn't want to just post all the links directly on the web, right? To avoid some trolls. So that was the only concern. But then feel free to reach out in case you find some trouble accessing these different Microsoft Teams rooms. And well, enjoy the poster session and the coffee break in our own place. But yes, also keep in mind that we have additionally, with respect to the different rooms of the different posters, also a social room, so we can just have some fun there and interact with each other. And we have also 1DB stand. So if you want, you can go there and talk with the weights and biases guys that will showcase some of their tools. And apart from that, I'll see you directly again at precisely at 11:10 Nashville time for the invited talk from Rehg. So I'll see you there, and we're not gonna close this live stream. So don't worry, you can just stay connected here, and the talk will start again from Jim at 11:10 on the same channel. So thank you so much, and I'll see you soon.
Hi, welcome, Jim. Could you try to share your screen and maybe check your microphone for the talk?
We cannot hear you. I think the
Jim, you are muted.
Yeah.
Okay, how about that? Better?
Yeah, perfect.
All right. All right, great. Let me see if I can share my screen here real quick. One sec. Okay, down here. Let's see. One second. Okay, can you see my first slide?
Yeah, looks perfect.
All right, and I think we're probably golden.
Okay, so first I'll be introducing you, and then you can go ahead. So welcome back, CVPR, and thank you for the amazing interactions in the first poster session. Now, the second session will be at 4 p.m. Nashville time. And so now it brings me to the honor of introducing Professor Jim Rehg. He's a professor in the School of Interactive Computing at the Georgia Institute of Technology, where he also is director of the Center for Behavioral Imaging. And in his lab, they focus on three main pillars. First of all, on computer vision and behavioral imaging and mobile health. And in the next 25 minutes, he will share with us his latest seminal works and his talk about repetition, reconstruction, and forgetting in continual learning. So give him your virtual applause. And Professor, the floor is all yours.
Great, thank you, Matthias. It's really great to be here, and I appreciate the opportunity. I'm going to talk about some work that we're doing with 4 graduate students in my lab listed. You can see them there below. One of the motivations for our work in continual learning really comes from an interest in understanding how infants acquire models and information about the world. And you can see an example of how an infant captured in a laboratory would pick up a toy and play with it. And we know that this kind of self-directed exploration is a key property of infant learning. And on the right, I list sort of 5 properties that we believe characterize infant learning. And these are all the areas that are a challenge, essentially, for computer vision and machine learning methods. And I'm going to talk about some work on the first 3 of these topics in my talk, and there are other aspects as well that I'm not going to get to. So we know that in continual learning, there's a useful framework in thinking about how a learner progressing through a series of tasks might encounter challenges. And this can be framed in terms of transfer. Forward transfer, when the representation you've learned at some point in time is carried forward to the next input batch of data, and that carry forward of the representation may allow you to learn that new concept more easily. Backward transfer refers to the fact that the thing you're learning right now may impact the representations that were learned in the past. And we're all aware of this problem of catastrophic forgetting, which arises in the case of negative backward transfer. What you learn right now negatively impacts representations you've already learned, causing the learner to forget important concepts. And so this has been kind of a key observation that has really shaped in a significant way the literature around continual learning. So one of the goals in my talk is to sort of look at a very specific setting on the one hand in continual learning, which is the setting of sequentially presenting to the learner a series of classes using a single head approach, meaning there's only a single task that the learner is trying to address. You can think about learning a set of object classes in a standard data set as being an example of that task. And although this is in some sense one of the simplest continual learning problems one might have, we know that there's a rich set of tasks shown with the red dots there in the picture that one can address. And we know that for all of these tasks listed there, catastrophic forgetting is sort of a key problem and a key challenge for the field. So what I want to do is sort of introduce to you some other tasks that one can address within the same setting, which have the interesting property that they don't seem to be plagued by catastrophic forgetting. That forgetting does not seem to be the same issue for these tasks as it is for the ones shown in the red dots. And the first set of tasks we're going to talk about are reconstruction tasks, where the learner's job is to take an input image often drawn from some class of objects. But instead of producing the class label, the job of the learner is to produce some other characterization or representation of the scene, like the shape, for example, or a 2.5D representation, or so on. And it turns out, as I'll show you, these tasks are actually quite different from the tasks on the left in terms of their continual learning forgetting properties. The second setting is one that we refer to as repeated exposures, where the tasks are coming to the classes are coming to the learner sequentially, but they're coming with repetition, so that when the learner sees a batch of data about a particular class, let's say, that's not the only time it's going to see that class. That class may come again in the future. And we'll show that these tasks that are defined by repeated exposures are also not subject to catastrophic forgetting. So let's go ahead and just sort of dig into this a little more and look at some of the details. So referring back to our kind of anatomy of infant learning, from that perspective, you can actually define an interesting kind of a variant on the standard sequential class task in CL. And this is the variant where the learner receives a batch of images about an object that are coming from contiguous views. Okay, so you might rotate an object, for example, in 3D and look at it. And this is kind of a nice problem for modeling actually what infants are doing. You can think about these kind of moments where you get a set of views are delineated by the event where the child picks up a toy and then puts it down or drops it and picks up another one. And so it turns out that work we're doing in CL can actually be very relevant in thinking about how infants actually learn from a stream of inputs. And we've been able to simulate this type of data using a data set and a simulator we created at Georgia Tech. And you can just see some of the examples here. This is the kind of training data, kind of rotating an object around a certain axis for a short sequence of frames, and then testing data, coming likewise. And then with this data, we can essentially frame this task of learning from repeated exposures as we allow the agent, in this case, like the simulation of the child, to pick up objects in some sequence at random. And this is kind of the finding from a paper we had in 2019, that in this repeated exposure setting, the learner actually does a very good job in reaching essentially close to the batch accuracy shown here in the top right. And in this example, there's 200 classes that are being learned. 20 things being learned, 10 exposures per object. And then, no, I'm sorry, 210. Yeah, that's that. I couldn't see the right the video. So 2,000 total, what we call learning exposures, where a mini batch of data is presented to the learner. And then this is coming from 200, objects. And then each of them is going to be repeated 10 times. Now, the order of repetition is completely random. You can see there with the black arrows showing a particular object, a car, the places where that car data was presented to the learner. So it's completely random over time. And the curve that you can see in kind of light purple, the dotted curve, denotes when the learner has seen, how many classes the learner has seen up to that point. And so when you get to a point about right here at 800, the learner has seen all the classes that are going to be presented in this experiment, but you can see the accuracy is still not as high as it's going to be as learning continues. So this suggests that forward transfer can be quite beneficial if you simply allow learners to access data more than once. And I would argue that this is a relatively practical and realistic paradigm for continual learning. It's probably unlikely that a baby or a robot examining items in its world is going to encounter important things just once, and have only one chance to learn the concept. So I think this is an important kind of variant to think about when you're designing kind of CL experiments. And this just shows that if you don't allow repetition, there's nothing sort of special about this data set of toy objects. The learners experience catastrophic forgetting in the single exposure case, where you get to see each object only once, just as we've seen with many other data sets. All right, so that's sort of looking at repetition as a particular paradigm for learning, looking at the impact of repetition on the continual learner's behavior. And I just want to point out that for these experiments, we're using what were kind of state-of-the-art continual learning algorithms a couple of years ago. These have the benefit of being very simple algorithms, just involving some memory that you use to store some exemplars, essentially a memory bank of exemplars to store some previously seen examples. So this is a very standard paradigm in continual learning, and one that has been used in many works. And so we're showing is that by simply placing these existing standard methods into a repeated exposure setting, we're able to get dramatically different performance results than we've seen in other settings like single exposure. So I want to turn now and look at another set of tasks that we haven't really seen before in a continual learning setting. And these are tasks involving reconstruction. And the starting point here is to look at a problem of single image 3D reconstruction, which you can see in this diagram. So the idea is that a single image comes in on the left. It's going to be processed by a module called MARNet, which is doing a kind of 2.5D sketch decomposition of that image, so producing a depth map, a silhouette map, and a set of surface normals. Those in turn go into a shape predictor, which is trained to take those inputs and then produce as its output a 3D representation of the object shape. Okay, so we're going to look at training these models not in the batch setting where they're typically done, but rather training them continually. And so in that case, the learner is going to get a mini batch of data from a particular class, and that data is going to contain the input image you see on the left and the paired 3D ground truth you see on the right, and it's going to learn to produce that 3D output with the given input. And then we're going to test that model as we go along and see how well it generalizes to unseen examples. So there are a couple of questions about representation here, and I just want to briefly talk about the 3D shape representation that we've adopted. So there's many choices, of course, for 3D shape. You can use meshes, voxels, point clouds, etc. But it turns out that a representation that seems to be quite powerful for these tasks is the one that you see on the right. It's known as a signed distance field. And the idea is that you represent the surface implicitly by describing the distance between a set of query points and the surface. So each of those points you see on the right at the top there in blue and orange, these are query points. Some of them are going to be inside the surface of the object, within the object volume. Some are going to be outside. And then each point is going to be assigned a distance, and it's simply the distance from that point to the surface. So given a representation of the object in this SDF format, you can then pass a set of query points into that representation. You can extract the associated distance field and then use an algorithm like marching cubes, for example, to reconstruct an equivalent surface mesh. And so the surface mesh you see there in brown is the surface mesh that marching cubes produces by analyzing the set of points in the signed distance field. So the advantage of this approach is that it lets us get a very precise description of surface detail without making kind of fixed decisions about, for example, voxel grid size, and without having to sort of, deal with point clouds and other kind of more complex representational choices. So this is an architecture from a recent publication. You can find it on arXiv. It's called SDFnet. It's simply a way to use the signed distance field representation to recover 3D shape from a single image. And so on the top, you see the input block of MARNet that we showed you before, and then that's followed by an encoder that takes the image and produces a latent shape feature vector. And that feature vector is then paired with a set of query points passed through another set of blocks, resulting in the prediction of the SDF values. And that in turn produces the 3D reconstruction associated with the input image. So we're going to be using this architecture for all of the subsequent experiments that I'll show you with continual learning. And one of the reasons for focusing on this is that this architecture currently has the best performance in the single image 3D reconstruction task. So this is just showing some qualitative results comparing our shape reconstruction architecture to some other previous state-of-the-art methods, and showing that qualitatively the meshes that we're getting look significantly better. And then we have some quantitative, quite a bit of quantitative comparisons in the paper as well. And I refer you to the paper for more details on that. So that's kind of the shape reconstruction performance. And then I just want to point out that what we're doing in using these 3D models for continual learning is we're actually rendering them in a relatively complex way. So we have a complete surface reflectance model. We're doing shading, ray tracing essentially to generate images from these 3D objects, and then placing them over randomly selected backgrounds consisting of real-world photographs. We're getting a relatively challenging image as a result of this rendering process. And ironically, this is kind of in contrast to a lot of the previous work in shape reconstruction, where people have tended to use relatively simple either Phong or Lambertian shaded models without very much surface texture and with very little in the way of complex lighting or background. So we've shown in our work actually that this realistic rendering actually makes shape reconstruction performance significantly worse than the case that has been kind of the state of the art up to now. All right, so that is a kind of an architecture for solving a task which is quite different from classification, where the goal is to produce a 3D representation of the object. And then one of the kind of findings that we thought was interesting and surprising is that this method, when trained in exactly the same way you would train a batch learner, so usually just vanilla SGD, exactly the same losses, no modifications or enhancements here to reflect the fact that this is a continual learning task, so no exemplars, no memory, etc. performs essentially without any forgetting. So you can see here the learning over a series of batches for this algorithm. This is looking at presenting 5 classes at a time in a single learning exposure using the ShapeNet Core V2 data set, that entire data set. So the performance here is not the same as batch performance. So it's not the case that there's no difference between continual learning and batch learning, but the standard kind of forgetting behavior, which is kind of trajectories over time where the performance drops off significantly due presumably to negative backward transfer, doesn't seem to arise at all in this setting as it does in the classification case. And you can see that there's a slight upward trend for this curve. And so we sort of stopped the process at this point, but you can imagine continuing this, and you can imagine this might actually increase over time and approach the batch performance. And that's exactly what we find. So this is now showing the repeated exposures case, where we're taking that same setup I showed you before, and now we're allowing the classes to repeat a certain number of times, again, in a completely random order over a longer series of exposures. And if you allow the learner to have this additional access to the examples via repetition, then we see that each of these different algorithms, essentially we're showing here, are essentially converging very close to their batch performance. So this suggests that this particular task of 3D reconstruction is not plagued by the standard kind of forgetting concerns that we would normally associate with continual learning. So this is kind of an interesting subclass or subcategory of continual learning problems that really hasn't been studied before. All right, so then you may ask, is there something special about single image 3D shape reconstruction or something special about our architecture that might be the basis for this task? And we've done some additional experiments to shed some light on this. I don't think this is yet an exhaustive characterization, but we looked at, for example, the 2D sketch estimator that we use as a pre-processing block in our shape reconstruction architecture. We looked at training that block also in a continual manner. So this is the same setting of single exposure, training the 2D sketch architecture, the MARNet architecture in a continual way. And we see once again that these learners don't experience, the 2D sketch learner doesn't seem to experience any catastrophic forgetting. Maybe in the beginning on the left, you can see a little bit of fluctuation, but this is probably within the realm of stochastic variability that we see in learning, anyway. And we're getting this nice behavior of increasing performance over exposure, even though you're training in a continual setting. The learner never sees more than one class at a time, just like it would in a standard sequential class kind of problem. All right, so that's kind of expanding a little bit the boundaries of how we think about continual learning and forgetting. And I want to then kind of piggyback on this and see if we can, build some additional capabilities with these tools. And before I get to that, one thing I forgot is we also looked at image auto encoding. Okay, so this is in some way the simplest, reconstruction task, if you will, where you just have a bottleneck and your job is just to encode the image and then reconstruct it at the output. We show this for CVPR 10, and we show that, again, this learner being trained to auto encode in a continual way doesn't suffer from catastrophic forgetting. So in this case, this is the reconstruction error, so lower is better, and it rapidly converges to quite a good performance on CVPR, and then it just stays there as you add more and more classes that learns to reconstruct. So this is kind of a sampling of tasks. Again, like I said, I don't claim that this is an exhaustive set as far as reconstruction is concerned, but I think it provides some interesting evidence for the qualitatively very different behavior of these learners in the continual setting. All right, so we thought about, could we try to connect a little bit the continual task, the reconstruction task to classification? Could we figure out a way to kind of leverage the learned representation of shape and see if that might provide some insights into what could be done for classification? So this is a kind of a initial experiment that I'm reporting here. The idea is to frame a classification task around the inputs to the shape reconstruction task, which is in this case depth maps and normals. So you're getting depth maps and normals coming in. You've already trained the shape reconstruction algorithm in a continual manner, and we take the layers that do the encoding from that architecture. So this is a learned feature representation that's been learned continuously that encodes shape. And we're going to take that representation and use that to build a continual classifier. And the way we're going to do that is we're going to use the standard nearest class mean classification approach. So we're going to take some exemplars that have class labels associated with them, map them into this shape-derived feature space, and then classify novel inputs by looking at the difference between those inputs in their mapped into the representation, looking at the embedding of those inputs, and then looking at their nearest class mean. So this is a standard thing that's used in iCarl and a number of other algorithms. And so if we do that, what we see is that this shape representation learned continuously is actually providing a fairly good representation for classification as well. So this is on ShapeNet 13, so it's a relatively small number of classes, but it's being compared here against a number of recent modern baselines, GDUM and so on, and another method called YAS that I'll show you in a second that we are introducing in this work. And it's exhibiting essentially competitive performance. These other methods don't have the benefit of the shape representation. They're being trained directly on the inputs, but then they have the ability to learn the entire feature representation continually as they go, which for forward transfer could be a benefit. So this is showing that the representation we've learned from via shape seems to be useful for this classification task, and thereby continual shape reconstruction might eventually be an interesting proxy task for continual classification. All right. So that's kind of trying to connect a little bit the shape world and the classification world, if you will. All right, so I want to now talk about, sort of turn and dig a little more deeply into classification. And this is the case where we know that, it remains the case that in the sequential, class single head setting where you have a single exposure to all of the classes, we know that catastrophic forgetting occurs, and our evidence and our experiments support that conclusion as well. And so a remaining kind of intellectual question then is to try to understand what is it about this setting in particular that seems to be so prone to forgetting. And one of the really nice ways to frame this question, which was really introduced in the really nice paper, the GDUM paper that we saw quite recently, is in terms of thinking about the benefits of backward versus forward transfer. And so we know that backward transfer has this negative risk that backward transfer can destroy previously learned representations. We know that forward transfer has a potential benefit that we can leverage a continually learned representation to make learning the next task easier, or at least to advance toward the goal of a completely learned representation. And GDUM sort of frames this dialogue but in a very specific way by saying, how about if we just throw away the representation at every time step, at every epoch or every learning exposure, we just delete all the weights and start them at random. And you can think of this as essentially preventing any kind of backward transfer. So backward transfer is gone through this approach, and that prevents any kind of forgetting. But you're also obviously losing the benefits of forward transfer. And then in the paper, what they show is that this algorithm outperforms many baselines. And that suggests that, in fact, the benefit of forward transfer is outweighed by the negative consequences of backward transfer. And so what I'm going to present to you now, and I'm just showing the details in this slide, is a very simple baseline, another one, which is actually performing forward transfer. So this is more in the spirit of all the other standard continual learning algorithms for classification that do forward transfer, that pay the price potentially for backward transfer. And the motivation behind this algorithm is to be as close as possible to batch learning, take as few kind of deviations from batch learning. And the main deviation is just the use of the exemplars that is there in all the other works that people have seen. But there are a bunch of very specific choices here about exactly how to set this algorithm up. And I'm not going to go into the details now, I'll refer you to our paper. But it turns out that these choices actually make a big difference, that sort of being really careful about some of these details can produce sort of qualitatively different performance compared, for example, to iCarl, which is also using exemplars in many ways, but differs from this algorithm in many of these kind of specific details. And so the main takeaway from this section is that once you do this sort of careful job, the comparison to GDUM is much more favorable in terms of forward transfer. That this YAS algorithm exhibits performance that I would claim is essentially equivalent to GDUM in the very specific setting of class sequential single head tasks. And in that setting, we actually see a slight performance benefit on CVPR 100. And then we see essentially equivalent performance on iNaturalist 2019. And you can see the specifics of these experiments in the top above these charts. And so this is an interesting finding, I believe, that suggests that the conclusion you might draw from GDUM is not as stark as you might have sort of imagined from that paper, although there are obviously many tasks that are covered in that paper that we're not talking about here. And it's not the case that forgetting is no longer an issue. So this is just another interesting data point, I think, to shed some light. So I just want to now show you some other results for YAS. So this is going back to our TOEIC 200. We see a performance benefit of YAS over the other baselines I showed you earlier for that task. This is looking at CVPR 60. And again, we're seeing a benefit of YAS over these other baselines like iCarl and so on. All right, so I want to just end by just digging a little more deeply into what's going on in terms of forgetting. And one of the things that we know is that these architectures tend to have two major components. There's a block, a series of ResNets that does feature learning that encodes the image into a set of features. And then these go through a pooling layer and are decoded into class labels by a fully connected layer at the very end in the head. And so one of the findings that I think other people have alluded to this as well, but we've done a nice job, I think, to really dig into this, is that most of the problem seems to actually lie in this FC layer, in the decoding of the final output into class labels. And that the representation you get through continual learning is actually better than you might expect if you just look at the class performance, in forgetting. And so one way to look at this is to look at what's happening within the learned activation. So there's this CKA method you're probably familiar with for comparing populations of activations. You can use this to compare architectures. So the top left of this slide shows CKA scores, essentially correlation scores between the output of the feature layer, the final feature layer for continually learned models compared to a batch trained model. And you can see a relatively high correlation with the batch trained model for a number of different architectures that we're showing here. But the key property is that correlation, after you get past the initial ramp up, that correlation doesn't change very much over time. So these representations are not actually changing very much in terms of their correlation scores against the batch model, even though, as you can see in the bottom right, the accuracy on these tasks is actually decreasing as we would expect from forgetting. So it suggests that forgetting may not be occurring primarily in the feature layer, but rather in the decoder of this architecture. Now, another way to look at this is to actually try to explicitly capture the concepts that are being learned in the feature layer without having to reference the classes. And I'm not going to get into all the details here, but the basic idea is we actually define a set of classification tasks that are defined in terms of just predicting the right activations in the layer that comes before the head. And then we can essentially produce a classification task that captures how well the visual concepts being learned by the feature layer are being preserved in forgetting. And if you look at the behavior of that graph, you can see that there's, again, a slight decline, but nothing like the class loss. And we're seeing after an initial period of ramping up in accuracy, the classification of these learned feature concepts independently of the class labels seems to be kind of consistently preserved over time. And the last way to get insight into this is to give the output, the FC layer or the head, the most opportunity that it has to learn the concept. And the way we do that is we take, after each round of learning, updating the feature representation, we take the continual learning, we take the class output, take the head, and we just randomly initialize it and then train it to convergence using all of the training data that has been seen up to that point. So we give the head access to all the data. And we're saying, here's a complete characterization of the classes. Do the best you can to decode the output of this learned feature representation, given the ability to sort of get the decoding correct. And what you see in that case is that the performance tends to be flat across these settings where otherwise there's forgetting. So this suggests that the head is where most of the forgetting is occurring when these models are being trained continuously. All right, so let me wrap up and just pitch a few small things here. So there's this data set I mentioned. It's a very large data set of toy objects that can be rendered in really nice kind of photorealistic ways. The main benefit of this over ShapeNet is it has almost twice as many categories. So it's very useful for kind of continual learning and other tasks involving category level recognition. We've got a recent paper that appeared earlier in the week in CVPR showing that this data set is actually very useful for doing single shot learning. So we can use shape representations, put them into a single shot learning architecture, and then get benefits over purely image-based training, suggesting again that kind of shape and shape bias can be a powerful cue for doing classification. And I refer you to this paper that appeared earlier for the details on that. And then I just want to plug a work that's currently under review that's out there that we're going to be releasing on archive soon on using a even more extreme version of this, essentially no multi-view supervision of any kind, so no explicit 3D supervisory information available to the learner. The learner simply has a single view of an object and the class label associated with that object. And then what this learner can do is leverage that semantic information, leverage essentially the supervision that comes from the class label, and then use that as a very weak form of supervision to learn shape reconstruction. And we're getting, in this case, very good results that beat a number of existing baselines on ShapeNet 55, which is quite a large data set of 3D shapes. So I think there's a very nice kind of story here for looking at shape and classification tasks in a simultaneous or a joint framework, and then using that as a tool to study some problems in continual learning. All right, so let me wrap up and then see if there's time for some questions. So just to conclude, I think we understand that there's a very specific setting where continual learning leads to forgetting. And this is the setting of single exposure, sequential class, single head architectures. But we've shown that if you enlarge that problem space to include repeated exposures, forgetting becomes much less of an issue. If you enlarge that class to include continual reconstruction tasks, forgetting becomes much less of an issue. And that this can be studied in a number of ways, as I've showed. And it seems to be that for the classification task, the FC layer is the major problem. And we provided a new data set and a number of algorithms and code that's on the web you can access to study these tasks. Thank you.
Thank you so much for the great talk. We have a couple of minutes time for some questions. So first of all, I think it's great you're also looking at these other tasks that have not been explored before. Also on this repeated exposure, one question came to mind for me is, how do you see this when, for example, how are these exposures actually defined? For example, if you have a very large data set, if you just would learn multiple epochs on this large data set, you could see each of these epochs also as like a single exposure to the data. So how does this compare to the setting you're referring to?
Yeah, so I think that's a really great question. And I thank you for asking it. And let me just kind of restate what I think you're asking. So it's clear that when you extend the repeated exposure setting, one way to look at that is you are bringing the paradigm of learning in some way closer to batch learning, because obviously the batch learner has the chance to see the concept classes that it's learning many times, i.e. with repeated exposures across many batches. But there is a crucial difference in the setting that we're framing here in this work, which is that any one mini batch only contains the data from a single class. So one would argue that, like in the standard batch learning setting, one of the major benefits of those mini batches that mix images from multiple classes, it allows the learner to figure out in one batch, as the weights are being adjusted, how to take into account, you know, the effect of one class and the other interacting in the representation. So it has this ability to kind of take a snapshot into the representation and understand how the different classes may need those features to be organized differently to produce high accuracy. And the continual learner with repeated exposures doesn't have that ability. It can't see in any single mini batch the interaction among the classes. And so then it has to do that only in the setting where you have all the data from one class and then another chunk of data entirely from a different class. And so I think you can look at this, you know, there are a couple of ways you can look at this. One is that this is kind of a generalization of continual learning into this setting, or you can look at that the batch learning actually can be, you know, generalized in some sense, you know, towards continual learning in a way that actually is quite effective. And you know, the reason I'm excited about this is I think for many applications of interest, like in our case, studying child development, this is a really natural paradigm, whereas the single exposure paradigm is really unnatural. Like it just doesn't resonate with things that kids, you know, can do. So, you know, single shot learning is very natural for kids, and learning with repetition is very natural for kids. And that's kind of where we want to go with our work. And I think you could argue the same thing for robotics as well.
Okay, thank you so much. There's still time for one question here from Terry Bolts on YouTube, the live stream. And he asks if like the 3D and 2.5D sketch, are they just really a single task? Because
yes,
objects or classes is not that relevant to the task since it should be true for any class.
So that's a great question. And let me give two answers to that. So the first answer is yes, it's just a single task. And I agree that one of the caveats for all these findings is this results on a single task. And we don't know what happens in the multitask setting for all the results that I showed. So that's an important caveat, and thanks for again emphasizing that. However, what we know from single image 3D shape reconstruction is that categories are actually really important, because one of the challenges in that space is actually defining generalization tasks that are sort of reasonable. And the evidence for that is that up until fairly recently, the state of the art for that problem domain was actually to mix training and testing examples from the same classes. And what you find if you do that for data sets like ShapeNet, for example, is that there are many meshes within a class that are actually very similar in shape. They differ only in a small amount. And so you actually have data leakage in that case. If you do the paradigm that would be a standard paradigm, for classification, you actually get data leakage, and it's actually label leakage, and it's actually an invalid experiment from my perspective. And so the only way to avoid that is actually take the data organized in classes where you say, well, these meshes are one class. They're going to be very different in terms of their qualitative properties than meshes coming from a different class. And if you test standard algorithms in this way, you get a substantial drop in classification accuracy. So the task of learning on a set of classes and being tested on a set of different classes for shape learning is actually a very kind of non-trivial problem in some sense for our current modern state-of-the-art shape prediction algorithms. And so that is a way of motivating why this sequential class paradigm is actually not kind of, let's say, trivial or no different from randomly mixing examples across classes. I don't have that last experiment to show you, but I'm pretty sure that if you did that, it would be a very different kind of level of performance.
All right, thank you for the elaborate answer and for your amazing presentation. I also want to invite you to the discussion panel at 2:40 p.m. if you have time. So you can just join in if you want on the same Zoom link here, and we would be happy to host you there as well.
Okay, yeah, I'm not sure offhand where I'll be at 2:40, but if I can join, I definitely will.
That would be great. Thank you so much. Okay, so that brings us to the next speaker. Rehg, could you try to put on your microphone and share your screen?
Hi, everyone.
Hi.
So
Seems to
that's the microphone task.
Yeah.
1 second. Okay. Do you see my screen? I'm trying to make a full screen.
Yeah, it's perfect.
Just
I can just see the
1 moment, sorry. Okay, 1 second. I'll just try to stop, make it full presentation first.
Okay, great.
Okay, how about now?
Yeah, works perfect. Okay, so let me first introduce you. The next speaker here is actually my former colleague at KU Leuven, Dr. Rehg Al-Youni, and she has obtained her PhD at KU Leuven's PSI lab with no more than 8 seminal works in the field of continual learning. And you may know her as the author of memory-aware synapses, expert gates, or maximally introverted retrieval. And as of today, she has been working for almost 2 years as a researcher at Toyota. So we are thrilled to host her in this workshop. And after this 25-minute presentation, with some time for questions after, she will also be joining the panel discussion at 2:40 p.m. Nashville time. So without further ado, Rehg, the floor is all yours.
Thank you so much, Matthias, for the great introduction. Okay, I hope the talk meet your expectations. So I'll speak more from someone who works closely with continual learning point of view. So I will try to give a storyline about the different settings of continual learning and their characteristics, how they evolve until what is the ideal setting. And then I'll try to widen the scope, look at closer problems to continual learning and see what insights, and maybe it's a message for you guys to start looking around also. So probably you have heard it, but it won't harm just to give a reminder for people who join. So continual learning studies the problem of learning from an infinite stream of data that are originated from changing input domains and possibly associated with different tasks. The word task is very vague, and we have suffered a lot at the beginning of this continual learning journey, that what is a task? And to me, it's just a group of classes, concepts, and actions that might have been related, but they are learned at one stage in time. So why do we need continual learning? We need continual learning because we want to accumulate knowledge over time. We don't want to redo the training at each time we see new data. We don't want to waste our time or resources and to facilitate future learning. So having this established, the first explored setting and most explored setting is what is called the task incremental setting. So we have this stream that is split it into a chunk of tasks, and I've already explained the task. So just the data that arrives at one time, and then the model will learn that offline. And then when it moves to a next step, then the access to previous tasks data will be prohibited. And then, as you know already, the main challenge is catastrophic forgetting if we just learn these tasks naively one after another. So the main focus was overcoming catastrophic forgetting. And then we started simple, very short sequences, no really strict memory compute constraints. And most importantly, the output layer was not shared. So for classification task, image classification, for example, each task has its own output layer, which made the problem much easier. Now, just a bit of an overview, there are different methods. So regularization-based method that tries to preserve what was already acquired by the model, either parameter regularization or functional regularization. And then you have the line of parameter isolation. So not really sharing of parameters. So once something is learned, is fixed, but then you have an expansion probably of the network to accommodate new information. Now, the main shortcomings is the multi-head setting, which means that we need a task oracle at test time. We need someone to tell us to which task the test sample belongs to. So if there is a clear difference in the input domain, that might be easy. We've tried to develop a solution for that. But if this is not the case, that's just only solving half of the problem. So, and then since this marginally meets application needs, the other more practical setting than the previous one is what's called incremental classification, or what I would call the shared head setting. So the main difference is now the output layer is not separate, it's shared among all classes. Now, since we have to learn something new and differentiated and discriminated from previous things without knowing what those are, so we need a kind of replay. It's challenging without it. So most works use experience replay or pseudo samples as memories of the past. Now, what I want to arrive at is that there has been a trend of methods that try to tackle the problem of bias in the last output layer. So it's papers suggesting that the last layer, the weight norm of the new classes is significantly larger than previous classes. And there has been coming with solution to tackle this problem. Now, what I want to hint is that this is a non-problem in long classification, that underrepresented classes will have a low weight norm. So what I'm questioning here, are we converting the problem of continual learning into a long tail classification that happens at each step? And then what are really the aspects of continual learning? So my just own personal feeling is that these boundaries or specifics of continual learning are a bit blurry here. So again, this requires offline training, large batches of data, so it only overcomes the head issue. Now, to me, what is an ideal, what is better setting or more practical setting that I would imagine and dream of is that we have an agent that is performing predictions or executing actions in the real world. And whenever new data became available, one samples or a few samples, a learning step can be issued. So we iterate always between training and prediction in an evolving environment. So in this setting, there shouldn't be a notion of task per se, at least to the learner. So we have a stream of data, and whenever data arrives, learning happens. We assume that it's an NIID, so the distribution can be changing smoothly or rapidly, or suddenly switching from one task to another. What is most important is the anytime performance. And I would like to focus on that for solutions to this problem. It's important that the method that we develop should be able to perform predictions on whatever has learned before at any point in time. So it's not that you can perform learning at offline or offline learning at separate steps in time. So now this setting that people and we started working on attract more and more attention, and people started, researchers started to define different characteristics of what a method tackling this setting should have, or what axes should we look at when developing methods for online continual learning. Now, everyone has his own list, but I would try to focus on few points shortly. That to me, the core is the limited memory compute. Without it, we can do offline training always. And then there are the axes that are related to the tasks. So the learner should not require, it can benefit, it shouldn't require knowledge of a task at training time or at test time. And there are the aspects that are related to transfer learning, so forward transfer or backward transfer. I believe everyone is familiar with. The other components that I think is really uncovered yet is the selective forgetting. So if we assume that we have a limited memory, then we cannot expect to remember everything. That's not possible, right? So it will be interesting and important that a method can identify which bits of knowledge or data that is embedded in the model can be erased to accommodate new information. So outdated information, things that are not used anymore, some kind of adaptation in the forgetting itself will be interesting. So we've tried to do something on that axis. There are some recent works, but I think it's highly relevant. The other aspect is the task revisiting, which I just mean that if we see samples from the past or that were represented in a past training steps, it would be appropriate if we know how to deal with that or with these kind of samples. So these characteristics, I think they move beyond the typical stability plasticity dilemma and open a lot of challenges. Now, this is a very challenging setting, online learning in a changing distribution, so it cannot really happen, or until now, without replay. You could think of exact replay of samples or generative replay, all is inspired by the human hippocampus. But generative replay makes a chicken and egg problem. And so far, I think experience replay is the dominant approach. However, neural memory and its study is quite interesting, but maybe it can be done along with the specific continual learning methods, or it can be seen as orthogonal. So in terms of experience replay, I would like just to focus shortly on two axes. The first is question of what samples to replay what samples to store in a buffer, if you think about exact replay, experience replay. And then, so what seems that all recent approaches use reservoir sampling. It's fine, it works quite well, but I want to note that in online continual learning, we argue that it's an IID setting. Now, our benchmarks, for example, MNSPlit, everyone knows, at each task, in fact, it's locally IID. At the end, the stream is uniformly distributed. So each class has equal number of samples. So reservoir sampling will perform well. But in the case of imbalanced scenarios where some samples are underrepresented, reservoir sampling will ill behave. And that's what we show here, that if we alter the sequence, change the distribution, reservoir sampling is not guaranteed to work well. And I would just encourage solutions to tackle this. And it's important not to really, in the experiment, mix methods that tackle this setting with other settings. So this is challenging, and we should also think of this. Just our benchmarks, sometimes everyone knows that, but sometimes fake what is really needed or what is really the best solution. So the other angle is what samples to replay. So we could naively, or we could just replay samples randomly. So when we receive an incoming batch, let's say in this example, a dog and a horse, we could just fetch a random number of samples, random samples from the memory, like an orange or a car, and try to learn an incoming batch. Now, I would think that will make more sense if we can retrieve the more related samples, like other animals that look like those that I'm learning in this case, of course. Now, this will make us learn stronger feature extraction, so stronger representation, and then also stronger decision boundaries. So we have tried that. So we try to retrieve the most related and maximally interfered samples, either using a generative model or just raw samples stored. For example, in the case of VIE, a 9 here as a new sample, we retrieve a 4 and a 3, so that they really look like it. And we think that will help the learning and improve the performance. We showed that. However, in current benchmarks, the gains are not so significant. I hope that in real scenarios with larger data sets, we can do better significantly than random replay. So now, apart from the particularity of experience replay, I would like to go a bit deeper. And in fact, I think now it's time to dig deeper into more interesting questions and the particularity of a solution. So what is really happening during learning, what causes interference, and moreover, what happens at transition points. So what happens when we see samples of new classes in the case of image classification. So in this work, we try to answer this question. We were curious what happens to the buffer data, samples that are stored, what happens to the representation when we see samples of new classes. So we investigated what we call the drift, the change in representation, and the gradient of the sample classes samples at transition points. You can see here, you see my mouse, hopefully. Maybe here, you can see that at transition points, this is the change in the representation. It's stabilized, and then when looking at new classes, you can see this jump that happens at each transition. Now the same happens when we see when we look at the gradients. So when we try to explain that, so in fact, this is a diagram illustrating what is going on. Let's try to explain. So if we have the red and blue points, those are samples from previous classes. They are well learned and well classified, like 1 and 2 in MNIST, right? So what happens when we see samples of new classes? Now, these green and purple dots. So one would expect that those will be easier if they arrange themselves, these new samples, and cluster together, and then they can be separated from previously well-learned samples. Now, in fact, what happens is the opposite. So we try to draw here, and this is what happens, in fact, the gradient of the loss. So for this red sample, given these samples circled in black. So what happens, in fact, is that the gradient coming from the previous classes samples are over-dominated by the new samples loss. So because the new sample loss is high, it will push every other samples away, and it will scatter the samples all around the space, and that will lead to catastrophic interference, which means we need more iterations to rearrange the samples after they were arranged already. And that's why we need large buffer. That's why we need more iterations. And in case of smaller buffers, we will have overfitting. We try to come up with a simple solution that we first learn the new classes samples still online in isolation, and then we leave to the buffer the adjustment of those newly learned decision boundaries with respect to previous classes. This simple solution has no extra computational cost, and in fact give us large gains in performance that we haven't in fact expected. It came out of surprise. So such a simple trick can do much improvement. And then in fact, it can be combined with other methods. So just message, try to dig deeper and look for insights to what happened at such a dynamic setting. So now I will try to move a bit to closely related fields. So far, continual learning has been studied in isolation. What are the links with other related fields? And are there insights to be uncovered when we widen the scope? So what I want to say is that now continual learning iterate between training and deployment, and we receive data we don't know from where. Now, if we would imagine the ideal setting of an autonomous agent, then let's start by training. So the model has been trained on a few classes, a few samples, and now it's being deployed. Now, if it's deployed in the world, it's always a changing environment. So small adaptation unsupervised can be helpful, or even a use of this unsupervised data to consolidate the past. What is more important is, since we assume that our knowledge of the world is limited because we need continual learning, then we need to detect novel input that does not belong to the current model knowledge. So a novelty detection component that can tell that, I don't know, the model does not know what is seen is important. Now, if we go to the training, it's important that we have something that can tell us what are the samples that are more informative, that are now unsure or uncertain by the model. Once annotated and labeled, they can improve the model performance. More importantly, these novelty detection input samples that we detected that the model does not know about, like new classes, those are likely to be annotated since they are seen in this world where the agent is acting, and then will be a new training step. So in this diagram, I have outlined different problems, right? So we have continual learning here, but it's closely linked to adaptation, to out of distribution detection, and active learning. So if those are nicely combined, we really get a nice autonomous or continual learning agent. And I would really like to see more of that. So I started myself. And then what we did is that we suggested to combine continual learning with novelty detection. So we want to have a continual learning method, so a model that is trained continually, prevent that with overcoming catastrophic forgetting. And then at test time, a method can always tell if something is new. So we combine continual learning with novelty detection. We are biologically inspired. So for example, in humans and mammals, the components of novelty detection and continual learning are tightly linked. So I'm no expert. Sorry?
You have 5 minutes.
Yeah, I'm on track. So I'm no expert in that, but what I've read is that studies shows that for novel objects, that the exploration time of these novel objects is significantly larger than things that have been seen before. So for a rat, when it sees something new, it goes explore it and try to learn about it. Now, this can be argued that it's unsupervised or other form of learning, but in fact, it's always linked. What is novel is going to be learned later. And I was motivated by this, and I wanted to see what happens if we do novelty detection in continual learning. So the main question is can we design a module, I prefer to call it like this, or a method that can tell at any point in time if a given input is relevant or represented by the current model knowledge. So what we did is that we constructed benchmarks similar to the sequences that we study in continual learning. And then we divided the sets that we should inspect into 3 sets. Now, for people who are aware of out of distribution detection or novelty detection, usually you have the inset, the samples that represent what has been learned before, and the outset. Now, at the continual learning, the inset here in green circles is expanding, but it's also shifting because samples are forgotten. So we constructed this second set of forgotten samples because it represents concepts that were encoded in the model and now they are forgotten. So somewhat erased from what the model has learned. So then the third set is the outset, which thinks that, let's say, in future tasks that will be learned in next steps. So we need to detect them. So I just want to show what we have. So for task incremental learning, so when each task in a sequence is different, in and out, green and red are easy to detect. Forgotten in yellow are quite mixed. But in the case of learning classes, so not really a notion of task or different domains, then the out samples are quite related to the in samples. And similarly for the forgotten samples that have been shifted from their clusters. So we need something possibly further than just using the output of the model to detect those. So what have we found? What we did is that we have established these benchmarks, tested different novelty detection methods, and with continual learning methods, different settings. So what have we found shortly? First is that continual learning challenges and increases the difficulty of novelty detection. So you can see here the performance that drops across the sequence, although we're using a continual learning method, and although that the N set is constructed from correctly predicted samples. So that's the increase in difficulty. And what we found, in fact, that only the simplest method works better than the more complicated design choices, which question the advances, and it somewhat tells us that we need something better for this setting. Also, that novelty detection methods can be seen as debugging tool for continual learning. So we've been finding things that are beyond, we think that are beyond the accuracy measures for continual learning. So for example, the first stage, the first step of learning has always better novelty detection method. Their samples, even if they were the first learned in the sequence. So what we say is that these samples were learned in isolation, while the other samples of new classes have been learned and have to be differentiated from or discriminated from previous classes. So the first step was the most stable learning, and thus we notice with different cases that its performance in relative to others is better, novelty detection performance. And then the last thing rapidly is that novelty detection itself as a method or a model need a mechanism to prevent forgetting. So here we show the accuracy of samples from previous stages of learning, and that's not accuracy, the novelty detection performance, and that's for the new recent stages at each step. So you can see this gap, and this is because of the forgetting itself, although the samples are correctly predicted by the model. So if the method uses directly the probability output of the model, it will benefit from the model's, the continual learning method. But if not, it should have something to prevent forgetting. So we think that the ideal solution is that novelty detection module should be directly coupled with the prediction model, so it can tell at any point in time what is relevant to this model and what is represented by it. So I really became fascinated by this, and I will encourage you to look at that. I think they are really coupled together and we can get more insights. So I came to the end. The key points from my presentation is that first, I think the stability plasticity dilemma is not the only challenge in continual learning. In fact, we think that there are inherently many learning problems that need to be looked at carefully. And also that continual learning should be combined with methods from other closely related fields. I mentioned novelty detection, but when we combine with other things, we can possibly reach the expected level of autonomy. Now, the other angle that I would like to see more research on that is what to do with samples of previous objects. So samples that have been, that their represented classes have been learned when they are encountered at test time, how to deal with that, how to consolidate previous knowledge. So possibly we can uncover more of continual learning and have less forgetting there. So those are the main points. I would thank you for your listening. I'm happy to receive your question.
Thank you so much for the great presentation. We have time for a couple of questions now. Maybe first one from Vincenzo. Do you plan to apply continual learning for autonomous driving at Toyota?
Yeah, that's why they hire me.
Okay.
No, I'm kidding. No, but I think that industry now are more like aware of continual learning, and it's really the key to have intelligence, like the first key. Of course, there are many aspects to consider, but if we cannot accumulate knowledge, if we cannot adapt new information and have like these dynamic models, there always be things to add, and we will never be able to solve the problem. So Toyota has many aspects. One of them is the autonomous driving, and I think that should be included even if we try. So that's always the question. If we try to annotate everything, right? If we're for a car that is driving on the road, if we try to annotate everything, and there will be a point where something new, like a new traffic sign is encountered. So a new traffic sign, for example, like a monowheel that we see now, it was not there before, or a scooter, or yeah, there has been lots of new types of transportation that was not there before. And then the question of, we have closed models, what do we do in these scenarios? So we cannot expect a closed world because our world is not like that. So continual learning is essential component, although we are not there yet, but I hope that at one point we should implement these methods. Yeah.
Okay, thank you. Maybe another question I think about is like, if you really want to apply these continual learning methods in like real world applications, like these autonomous vehicles, like more legal problems where, like, if a car is released now, it needs like certain kind of certification with like the car suffices on these certain criteria. But if we really want these adaptive models that are evolving while they are driving, we don't really have this kind of certainty anymore. So
yeah, I totally agree. So that's the main obstacle, is that for autonomous driving per se, you need to pass certain levels of safety. And then if you are changing your model, then there are certain questions. So I don't know how to deal with that yet. I just know it's necessary at some point. But yeah, this is more of a legal issue, or how to deal, how trust such a system. But this is why I think that the novelty detection component, was the transparency component of a model, also for autonomous driving, plays an important role. So, so for example, if the model can tell that something is out of its what it has learned before, like this is a new object, this is a new scenario, please help, then that become quite crucial. Right? So because then we can ask for human intervenence, and then it becomes less of a problem. Now, autonomous driving is one application, but there are so many other applications. For Toyota, it has this woven city. It's a smart city with all levels of intelligence. So in autonomous driving, it has its own particularity regarding this kind of safety when the car is taking control. But that's because we haven't trusted this technology yet. But does a human have no error at any point? No, there is like 10 to the power of minus 4 error in an hour. It's very low, but there is something. So yeah, either we program everything and we be sure of everything, or we will expect a bit level of yeah, tolerance. Yeah, I'm no expert there in these legalization steps, but I think we should be more yeah, open towards adaptive model and not really static model, because intelligence to me means something that can adapt. But yeah, that's my own perspective.
Okay, thank you so much. We have still one question left here. So in the YouTube stream, Ale Akrami posed a question. Thank you for the great talk. If we have outliers in our data sets, how should we handle them and separate them from null samples?
Yeah, so that's a great question. Thank you. So then the other question is, what is an outlier? Now, is it a mislabeled example or something that we shouldn't learn? Or it's something that is not, yeah, so probably mislabeled. Now, that's a problem of learning itself, how to deal with outliers, and it can be composed with continual learning. I think so far solutions of continual learning, and we have stated that before, that we don't really need deal with outliers. So they do happen, but we hope that the data set or the samples that we are learning, they don't contain much outlier. But the thing is that, or the main assumption is that when you learn and you don't have much to space or capacity, then you would focus on the regular and shared patterns among the data. So outliers will be harder to fit, and thus will be subject first to forgetting. And that's, I think, what I've seen before, that samples that really look different from the norm of a class, those are more like that are the boundaries of the decision boundary in an outlier would be even far. So this will be the first subject to forgetting, but I think then it's not a problem that we forget them. So maybe I haven't worked on that. I think it's interesting, but I think it's not the most problem of continual learning. Unless we want to remember everything, then it becomes an issue.
Okay, thank you so much for your answers on the questions and for your great talk.
Yeah, thanks.
Now it brings us to the last talk, which is actually a paper oral. So maybe Chen-Hei, if you could try to share a screen and put on your microphone. So also for everyone on the YouTube live stream, we've been receiving questions where you can find the slides. So the slides will be available on the main website after the workshop. And we'll also put the link to the main sites in the chat so you can easily access it. Okay, in the meantime, Chen-Hei, can you try to speak up? At the moment, I can't hear you.
Can you hear me?
Yeah, now I can hear you. Perfect.
Oh, perfect. Can you see my screen?
Yeah, I can also see your screen.
Oh, thank you.
I'll first introduce you, and then the floor is all yours. All right.
So I will begin my talk.
So I will first introduce you, and then you can start your talk.
Oh, yeah.
Okay. So to our pleasure, actually, we have had many continual learning papers being submitted to our workshop this year, as Vincenzo showed in the first words. And we found 2 works to really stand out, and they got some reserved time for an oral presentation in our workshop. So this first work being presented will be about a tale of 2 CILs, and the talk will be given by the first author, Rehg Chen, and he's affiliated with the Institute of Computing Technology in Beijing. So your screen is ready to go. So Rehg Chen, the floor is all yours.
Okay. Thank you for your introduction. So I'm Chen He from the Institute of Computing Technology, Chinese Academy of Sciences. And today I'm going to show our recent work on class incremental learning. And I'll tell you a story between 2 closely connected fields, class incremental learning and class imbalanced learning. And let me introduce you the 2 main characters, the 2 CILs. Actually, these 2 words have exactly the same acronyms, CIL. And we, for disambiguation, we use these 2 words to denote them respectively. As for class incremental learning, new classes arrive continually, and the model needs to recognize more and more classes. It is commonly assumed that the memory is limited, so only a small number of old class exemplars can be stored. Compared to that, there are a large number of new class samples. It is actually a class imbalanced learning problem. On the other side, the class imbalanced learning is an independent field with a long history, and the famous phenomenon in this field is that the variance of the minority class is likely to be underestimated. Therefore, the decision boundary biases towards the minority class. as can be seen in the picture on the left, since the training samples of the minority class are fewer, so the learned decision boundary biases towards the minority class, and the goal is to turn this one into this one, an unbiased classifier. There are two different solutions to this problem, and they are the data level methods and the classifier level methods. And after introducing our two main characters, here we will show you the connections between them from the following parts. First, I'll show you the relationships between anti-bias techniques in class incremental learning and techniques to tackle class imbalance in class imbalance learning. And second, we are interested in whether inspirations could be drawn from class imbalance learning to help us design new methods for class incremental learning. And third, we want to understand why these techniques work. As for the first part, here I show you a panoramic view of the anti-bias techniques in recent class incremental learning methods. Interestingly, we found that these techniques share some similar ideas with class imbalance learning, shown here. Taking the most famous ICAR, for example, the main building block is the NCM classifier, which is very similar to the prototypical network in few-shot learning. The NCM classifier is simple. No matter how many samples are, they just aggregate the samples of the same class into a single prototype. And then at test time, for a sample, they just predict the label by finding the most closest prototype it belongs. And in our paper, we show two different views to help us understand how NCM works. And here we only show a parametric view. Assuming that the prior probabilities are equal for each class and each class is multivariate Gaussian distribution, we can find that the decision boundary is quadratic. So it is hard to tell if the biasing phenomenon happens or not. By assuming that the covariance matrices are equal through mathematical derivations, we can find that the distance between the two class means and the decision boundary is equal, indicating that the bias is alleviated. By further assuming that the covariant matrices are isotropic, we can finally derive the form of the NCM classifier. And in the second part, I want to introduce a very simple technique called post-scaling, inspired by class imbalance learning. And it is based on the assumption that neural networks estimate posterior probabilities if Somax cross entropy is used. Through some mathematical derivations, we finally arrive at a very neat and simple form, which is simply to add an actual term to the logits. And the idea behind it is to compensate for the prior shift. The prior shift means that the prior probability for each class in the training and the test datasets are different. As for the performance comparison, here we show the top one accuracy for several class incremental learning and class imbalanced learning methods. Note that for some methods, there are actually two numbers separated by the slash symbol, which indicates the accuracy before and after the anti-bias techniques respectively. From these numbers, we can see that anti-bias techniques do matter in boosting performance, which means that the number after the slash sign is much higher than this one. Also, from this table, we can find that in general, these two methods are very effective For those of you that are not familiar with MDF-CIL, the idea is to let the weight vectors of old and new classes to have similar norms. Besides performance, we are also interested in the efficiency of these methods, so we recorded the running times. And from this table, we can also find that these two methods are very efficient. They have a shorter time. So judging from both accuracy and running time, these two methods are very effective and efficient. But why do they work? Do they really work as what the illustrate diagram shows on the left? Which in this illustrate diagram, the decision boundary bias towards the minority class, which is the old class in class incremental learning. And the anti-bias technique seems to move the bias classifier, the W hat, to the unbiased classifier, W star. But this is only an illustrate diagram. We want to show the real one. So we use some visualization tools. In this page, we first select a pair of classes, and we want to see that how the decision boundary changes before and after the bias correction. As for post-scaling, we show these violin graphs. These violin graphs show the distribution of the distances of sample to the decision boundary. Note that the red solid line is the old decision boundary, and the red dotted line is the new decision boundary after bias correction. The x-axis indicates the split of the dataset. Note that for the training split, the old decision boundary actually separates the two classes pretty well. But for the test set, this old decision boundary is actually inside the distribution of this orange class. But after bias correction, the new decision boundary is much better. As for MDF-CIL, the conclusion is almost the same, but we found interestingly that these methods actually rotates the decision boundary towards the majority class. In these figures, we show the polar charts, the polar charts show the distribution of the angles of the samples. We can see that the old decision boundary actually rotates anti-clockwise to the new decision boundary, and the new decision boundary is much better. So far, we have go through 3 different parts, and we know that these two learning paradigms, class incremental learning and class imbalanced learning, are highly correlated. The merit is that inspiration could be drawn from related fields in order for us to design new class incremental learning methods. But the downside is that the class incremental learning seems to degenerate into a class imbalanced learning problem. So what are the exclusive problems in class incremental learning? And here we offer some of our preliminary thoughts. And finally, I'll give some take-home messages. Judging from both performance and efficiency, we recommend these 2 methods first for class incremental learning. And second, through our visualization, we find interesting connections between these 2 methods. They actually rotate or translate the decision boundary towards the majority class. And finally, we need to reflect upon the exclusive problems for class incremental learning. So that is all for my presentation. Thank you for listening.
Thank you so much for the great presentation. We still have time for a quick question. So there's in the YouTube live stream, Ahmad asks if class imbalance is the same as a long tail distribution.
Oh, I think they are just describing the same thing but use different names. There are actually two fields called, one is class imbalance learning, and another one is long-tailed recognition. I think they share some common techniques to tackle this the class imbalance problem.
Okay, thank you very much. You can stop sharing your screen now, and thanks again for the presentation. So this brings us to the 1 hour lunch break. So the second part will be also live streamed on YouTube, but in another YouTube live stream. We will post a link in the first part now, so you can just easily redirect. So make sure to check that out. And you can also find it on our website. So I would say we had a very successful first part of the workshop, and hope to see you in 1 hour, and have fun in the lunch break. See you.